Every Honda Civic begins on a high-speed production line where precision and human engineering come together in perfect sync. From raw steel panels stamped with force to engines installed with millimeter accuracy, the entire process is built for efficiency and reliability. Today, we'll take you inside the factory to see how one of the world's most iconic cars is made from start to finish. To understand the making of a Honda Civic, we must start long before the wheels ever touch asphalt. At the very genesis of the production journey, the press shop. It is here, in a thunderous hall lined with towering metal-forming presses, that raw coils of rolled steel arrive from trusted suppliers. These steel coils, typically delivered on massive trucks or freight trains, are carefully quality checked for thickness, tensile strength, and surface consistency. Technicians inspect the incoming steel with precise ultrasonic and magnetic sensors, looking for any hidden flaws that might affect structural integrity. Once verified, the steel coils are loaded onto an unwinding line and fed into massive blanking presses, machines that slice sheets to exact dimensions for body panel stamping. This stage is not about shape yet. It's about preparing the right size of metal blanks that will later be contoured into the Civic's recognizable exterior components. Each blank is fed robotically into a deep draw stamping press, some of which exert more than 2,000 tons of force in a single downstroke. These presses contain die sets, essentially giant molds machined to micrometer tolerances, which shape the flat blanks into complex three-dimensional parts: doors, hoods, quarter panels, floor pans, and roof skins. The stamping process is both violent and elegant. With each press cycle, a blank disappears between the dies, emerging seconds later with ridges, folds, and curves now embossed into the once flat steel. Robotic arms then transfer these parts to stacking racks with vacuum grippers, organizing them for their next destination, the body shop. If the press shop is the forge, the body shop is the sculpture studio. It's here that the Civic begins to take on its distinctive silhouette. Using a mix of robotic welders, jigs, and human technicians, the various stamped body panels are aligned with incredible precision. Fractions of a millimeter make all the difference in structural rigidity and door fitment. The underbody is constructed first. Floor pan, frame rails, and cross members are robotically welded together in massive fixtures that hold them square. These sub-assemblies are then mated with the upper body structure, including the firewall, roof bow, and side panels. The process of joining these panels together is an art form in itself. Honda uses a combination of spot welding, where copper-tipped electrodes pass current through panels to fuse them, and laser welding, which offers even greater strength and less distortion. Each Civic contains thousands of spot welds, each one measured by inline sensors for penetration, pressure, and temperature. In certain areas, structural adhesives are also applied robotically before parts are pressed together, increasing torsional stiffness and reducing vibration. As the body shell, now called the body in white, progresses through the line, it moves through various stations where more components are added: inner reinforcements, mounting brackets, and crash structure members. Robots ensure these parts are always placed in precisely the same position on every vehicle. The body is then passed through a computerized vision inspection system, which scans it in real time for dimensional conformity. If anything is off, even by a millimeter, it is flagged and corrected immediately. With the body in white completed, the Civic now advances to one of the most critical and carefully controlled areas in the factory: the paint shop. Before any color can be applied, the raw steel must be prepared with a meticulous cleansing process. The car shell is first subjected to a multi-stage bath sequence in giant dip tanks that use alkaline detergents to remove oils, dust, and microscopic particles left over from stamping and welding. The shell is rotated robotically through each tank, allowing it to be completely submerged. and ensuring even coverage across all surfaces, both exterior and hidden interior cavities. After cleaning, the body enters an e-coat bath, short for electrophoretic deposition coating. In this step, the shell is electrically charged and dipped into a tank filled with a water-based primer containing corrosion-inhibiting particles. The electrical charge causes the primer particles to be attracted and evenly bonded to the body's surface. This layer not only improves paint adhesion, but provides crucial rust protection, especially in inner cavities that are hard to reach with spray guns. Once the e-coat is cured in an oven at around 180 degrees Celsius, the Civic moves into the primer application booth, where robotic arms spray a base primer coat across the shell. This step evens out the surface texture and prepares it for color paint. Following a short curing phase, the vehicle is moved into the color booth, a climate-controlled, dust-free chamber where the final paint coat is applied. Each Civic model has its own unique paint codes, which are carefully loaded into robotic arms that spray layer upon layer of base coat and clear coat in a highly choreographed dance. The painting process is arguably one of the most mesmerizing stages to witness. 12-axis robotic arms glide effortlessly around the car body, their movements pre-programmed down to the millisecond, ensuring consistent paint thickness and flawless coverage. The color coat is followed immediately by a layer of clear coat, which adds depth and gloss while protecting the finish from UV light and environmental damage. After curing in a second oven for up to 40 minutes, the freshly painted Civic body emerges gleaming, but still empty. Just a hollow shell with no glass, no engine, no wheels. That's about to change. The next phase, phase, is the trim and chassis marriage line, where the Civic's raw body begins to transform into a fully outfitted vehicle. This is where thousands of individual parts, from wiring harnesses to dashboard assemblies to seatbelt retractors, are installed piece by piece, each in a strictly orchestrated order that has been optimized for both ergonomic efficiency and production speed. Before any of that happens, however, the body must be precisely prepared for the installation of glass. Robots apply urethane adhesive beads around the front and rear window openings, and then suction-equipped robotic arms carefully position and press fit the windshields and back glass into place. Smaller fixed windows are installed similarly. These adhesives not only secure the glass, but also provide structural rigidity and watertight sealing. Inside the cabin, the assembly line team begins installing sound deadening mats, interior wiring looms, dashboard subframes, HVAC ducting, and insulation panels. Every cable must be routed correctly through predefined paths using color-coded guides and clips to avoid interference or rattling. Robots and technicians work side by side. Robots handling repetitive or awkward tasks such as bolting down seat frames or placing door wiring clips, while humans complete more dexterous jobs like feeding dashboard harnesses through tight spaces. In a parallel part of the factory, just as precise and choreographed as the main body line, the powertrain assembly line is busy bringing together the mechanical heart of the Honda Civic. Here, in a series of carefully timed workstations, the engine block, cast from aluminum alloy at an off-site foundry, is delivered for the beginning of what will become a highly intricate construction process. The raw engine block, a silvery rectangular core with machined bores and passages, is first mounted to an adjustable rotating stand that allows technicians and robots to access all angles of the component with ease. Technicians begin by installing the crankshaft, main bearings, and connecting rods, each component measured to precise tolerances using torque wrenches and digital sensors. The pistons are inserted and aligned with the cylinders, lubricated and checked for correct seating before the cylinder head is mounted and bolted down in a strict torque sequence. Fuel injectors, spark plugs, oil pans, gaskets, and camshafts are all installed in sequence. Robotic arms place timing chains or belts, set cam phasing, and verify timing alignment using vision inspection systems that reference QR codes and part markings. Once complete, each engine goes through a cold test station where sensors check oil circulation, compression ratios, and component tolerances without actually firing the engine. If the unit passes, it continues down the line to be joined with the transmission, either a continuously variable transmission, 6-speed manual, or in some markets, a traditional automatic. These transmissions arrive from specialized Honda transmission plants and are pre-assembled with clutches, gears, and hydraulic valve bodies already in place. The marriage of engine and transmission is done with the help of alignment jigs and torque-monitored bolt drivers to ensure perfect balance and alignment. This combined powertrain module is then sent via automated guided vehicle to the chassis line, where other sub-assemblies such as the front subframe, suspension arms, steering rack, and exhaust system are already being built up. In this stage, the Civic's front and rear subframes are assembled separately, each housing the relevant suspension geometry, control arms, sway bars, and dampers. These are pre-torqued and inspected before being mated to the powertrain and chassis cradle. Once this fully assembled underbody unit is complete, it moves via overhead conveyor to the marriage station, a dramatic intersection of the trim line and the chassis line. The painted body shell, with dashboard and interior partially installed, is suspended above the cradle. Slowly, the two converge. Using laser guidance and a complex hydraulic lift system, the car body is lowered onto the powertrain module with millimeter precision. Specialized guide pins ensure perfect alignment, and robots immediately begin bolting the chassis and body together at multiple mounting points. This process, known as the body drop or marriage, represents one of the most pivotal points in the Civic's construction. In just a few minutes, the car transitions from a hollow shell to a complete vehicle with drivetrain, suspension, and steering components now integrated. From here, the assembly line continues with intense precision as the Civic begins to come alive, inch by inch. The next station involves connecting electrical harnesses and fluid lines. Large modular connectors are snapped into place, linking the vehicle's main computer systems, ECU, sensors, transmission control, and lighting. Brake lines, fuel hoses, coolant pipes, and air conditioning refrigerant lines are connected with quick coupling fittings that are color-coded and pressure-tested for leaks. Robots insert and fasten fuel tanks underneath the chassis, followed by heat shields and underbody panels that protect the car's systems from road debris and temperature extremes. Meanwhile, technicians inside the vehicle are installing the instrument panel, infotainment system, airbag modules, and steering wheel. The center console and infotainment head unit are test-fired on the spot, using a temporary power source to ensure all touchscreens, audio systems, and onboard diagnostics are functional. Seats arrive pre-assembled from a separate supplier and are robotically positioned, bolted down with monitored torque drivers, and electrically connected for airbag and heater functions. Simultaneously, the doors, which were removed earlier in the process to improve access during interior assembly, are now reattached by a series of 6-axis robots. These machines lift the doors from their carriers, align them to body datum points, and bolt them onto reinforced hinges with a precision that's been pre-calibrated using 3D body scans taken earlier. Technicians then install seals, trim pieces, weather stripping, and window regulators before the power windows are connected and tested electronically. Next comes the installation of exterior lighting. Headlamps and taillights are snapped into place with molded brackets, fastened with screws and bolts, and connected via waterproof electrical connectors. Each light module is briefly illuminated to confirm functionality and correct alignment. The front grille, bumper fascias, and underbonnet components, such as the air intake ducting, battery, and fuse boxes are added next. Every step in this stage is monitored in real time by a central production server that tracks torque readings, scan codes, and pass/fail diagnostics from every tool on the line. With nearly all physical components in place, the Civic is almost complete, but not quite ready to leave the line. Next, the wheels and tires are installed. Tires arrive from Honda's tire supplier, already mounted and balanced on alloy wheels. They are indexed and attached to the hub assemblies using robotic wheel guns calibrated to apply the exact torque specification for each lug nut. These specs vary depending on wheel size, market, and drivetrain layout. An automated alignment station immediately follows, where high-speed cameras and laser sensors measure and adjust toe, camber, and caster angles on all four wheels. These adjustments are performed automatically by robotic arms that adjust the suspension linkages without human input. The engine is now ready for its first breath of life. The car is filled with all necessary operational fluids: engine oil, transmission fluid, coolant, windshield washer fluid, brake fluid, and refrigerant. These fluids are dispensed using automated boom systems that identify the vehicle model via RFID tags and fill to precise volumes using flow sensors. Then, the Civic moves into the initial startup bay, where for the first time, its ignition is triggered. An onboard computer runs a rapid series of checks on fuel pressure, ignition timing, emission systems, and electrical networks. If any error code is flagged, the vehicle is diverted for diagnostics. If everything checks out, the Civic proceeds. Following startup, the vehicle undergoes a dynamic rolling test on a set of inline dynamometers. The car's wheels are driven at varying speeds while technicians monitor acceleration, braking, gear shifting, and engine response. Noise, vibration, and harshness levels are recorded using microphones and vibration sensors in key areas. The vehicle's radar, sonar, and camera-based safety systems, like lane keeping assist and adaptive cruise control, are also calibrated using test targets and moving objects. Even the horn and windshield wipers are tested as part of this comprehensive validation. Once mechanical systems are signed off, the Civic advances to the water test booth, an enclosed tunnel fitted with high-pressure nozzles simulating rain and storm conditions. The car is sprayed for several minutes from all angles to ensure no water leaks into the cabin or trunk. Any intrusion, however slight, results in the vehicle being pulled for resealing and retesting. After the water test, the Civic passes through the final inspection bay. Here, a team of trained inspectors examine every surface of the car under bright, full-spectrum lighting to detect paint imperfections, panel misalignments, or blemishes. Doors, hoods, and trunks are opened and closed repeatedly to confirm proper fit and latch operation. Interior materials are checked for stitching quality, switch function, and material alignment. Even the scent of the cabin is evaluated to ensure consistency with Honda's brand standards. Once it clears final inspection, the Civic is driven briefly to a short holding area where any software updates are flashed into the ECU, infotainment system, and onboard diagnostics. The vehicle's VN is laser etched into the frame and stored electronically in Honda's global database. The car is now officially considered production complete. With the vehicle officially signed off from the production line, the next phase of the Honda Civic's journey is handled by a specialized logistics team responsible for organizing and staging vehicles for transport. At this point, every Civic has its final configuration, its color, trim level, engine variant, transmission type, and region-specific features all set in stone. But before it's shipped off to a dealership or distribution hub, it enters what's known as the Vehicle Outbound Logistics System. In a vast open-air vehicle yard adjacent to the assembly facility, often spanning hundreds of acres, you'll find hundreds, even thousands of freshly minted Honda Civics parked in rows that stretch toward the horizon. This yard is not simply a parking lot, it's a tightly managed inventory control zone that functions like a living spreadsheet. Each Civic is tagged with an RFID chip or barcode label that links to a digital manifest. These digital profiles contain everything about the vehicle: where and when it was built, its VIN, trim level, market destination, port of discharge if being exported, and even its assigned dealership. Before entering this staging area, each vehicle is given a final scan at the gate. This scan confirms the completion of software installation, quality checks, and fluid top-offs. Once scanned, a logistics automation system assigns a parking spot based on the vehicle's outbound path. Cars, headed for rail transport, are parked near the loading tracks. Those bound for container shipping are staged by the dock ramps. Regionally distributed vehicles are positioned near road freight terminals. Each parking operation is choreographed with the help of a fleet of vehicle movers, some human, some automated. In newer facilities, autonomous electric tugs shuttle completed cars to their assigned staging rows, minimizing fuel usage and reducing human error. As the Civic arrives at its designated position, it is double-checked for cosmetic integrity. No scratches, no dents, and no contaminants like bird droppings or sap that could damage paint before delivery. Depending on the region, the vehicle may receive a light protective wrap, plastic sheeting on the hood, roof, and doors, as well as foam bumpers or wheel covers. These additions protect the finish during transport, particularly when Civics are being shipped across long distances via rail or ocean freight. From here, distribution diverges based on geography. Civics bound for nearby regions are typically loaded onto multi-level auto transport trucks, known as car haulers, using a hydraulic ramp system that maximizes vertical space. Each trailer can accommodate 8 to 10 vehicles, depending on size and configuration. Loading these haulers is a skillful job. Drivers must navigate tight clearances, especially when reversing a Civic up a narrow ramp just inches from another car's bumper. Once secured, the transport trucks depart along pre-planned routes, tracked in real time with GPS and monitored for weather, traffic, and delivery schedules. Vehicles typically arrive at regional distribution centers or directly at dealerships within 24 to 72 hours of departure, depending on distance. But for Civics headed overseas, the process is even more elaborate. Vehicles scheduled for export are transported to a port of exit, usually via rail. Special rail cars, called autoracks, are designed for this purpose. They're 3 levels high and feature secure wheel chocks, enclosed sides to protect from the elements, and locking mechanisms to prevent vehicle movement during transit. Before boarding the train, each Civic goes through a brief pre-rail inspection, checking tire pressure, door latches, and fuel levels. Vehicles must carry just enough fuel for loading and unloading, nothing more. Once the autoracks reach a port, often within a few days, the Civics are offloaded and prepped for ocean shipping. At the port, Honda works with marine logistics providers to board the vehicles onto roll-ons or roll-off vessels. These are essentially floating parking decks that can carry thousands of cars at once. A team of stevedores and vehicle handlers drives each car onto the ship via massive loading ramps. The cars are parked tightly together, locked down with wheel straps, and catalogued by location and destination. Each ship carries a mix of vehicles headed to different global markets, with each deck subdivided by destination. During the sea journey, which can last anywhere from 2 to 6 weeks, depending on the destination, the vehicles remain dormant but protected. Temperature, humidity, and salt exposure are controlled to prevent corrosion. Some ships use dehumidification systems to further protect sensitive electronics and cabin components. Upon arrival at the destination port, be it Vancouver, Rotterdam, Sydney, or Tokyo, the Civics are offloaded and moved to an inbound vehicle processing center. Here, local Honda representatives carry out market-specific inspections and final preparations. Depending on regulations and consumer preferences, some components may be installed at this stage. Market-specific infotainment systems, badges, labels, or compliance stickers. The battery is checked, tyre pressure adjusted for the regional climate, and the vehicle is detailed one final time. Then, and only then, does the Civic make its final trip to a dealership, where it will be test-driven by prospective buyers and eventually become part of someone's daily life. The journey from raw steel coil to showroom floor is now complete. But behind this process is something even more impressive than the car itself: the manufacturing ecosystem that made it all possible. Every Honda plant, whether in Canada, Japan, the United States, or Thailand, is a model of lean manufacturing. Honda is one of the pioneers of flexible assembly, meaning the same line that produces the Civic may also produce other models with minimal downtime between them. This flexibility allows the plant to respond to shifting market demands without reconfiguring the entire factory. The chassis platform used by the Civic, for instance, might also underpin the Honda HR-V or Insight, all of which can be built on the same line with different modules and components swapped in real time. This orchestration relies on an advanced system of just-in-time supply chain logistics. Rather than stockpiling parts on site, Honda's suppliers deliver components like dashboards, seats, HVAC modules, and wiring harnesses exactly when they're needed, often arriving at the plant just hours before installation. This minimizes inventory costs and allows for rapid changes to production volume or specification. Each component comes pre-labeled with a digital build sheet that identifies exactly which Civic it's meant for, ensuring flawless sequencing on the line. Complementing this is the just-in-sequence system, which goes one step further, delivering parts in the precise order of vehicle production. For example, if the assembly line is building a red Civic Sport, followed by a blue Civic X, the bumpers, headlights, and infotainment units for each car arrive in that exact order, pre-arranged for immediate installation. It's a ballet of logistics that requires real-time communication between Honda's central production servers and hundreds of Tier 1 and Tier 2 suppliers. To keep everything running smoothly, predictive maintenance is used throughout the plant. Equipment sensors track vibration, temperature, load, and wear in everything from conveyor belts to robotic welders. When a part shows signs of fatigue, the system schedules preventative maintenance before failure can occur, reducing downtime and improving safety. Quality control doesn't end once a vehicle leaves the line. Each factory maintains a dedicated audit station where randomly selected Civics are pulled for intensive testing. These vehicles are dissected and reviewed by expert inspectors who examine weld quality, paint thickness, body fitment, software behavior, and road performance. This data is fed back into the production process to flag trends or emerging issues, enabling Honda to respond proactively and maintain consistent quality. In terms of environmental responsibility, Honda's Civic production lines are engineered for energy efficiency and waste reduction. Water used in the paint booth is recycled through filtration and reverse osmosis systems. Paint overspray is captured by electrostatic filters and reused. Waste metal from the stamping plant is sorted robotically and returned to the steel mill for remanufacturing. Even the heat from curing ovens is repurposed to warm other parts of the facility. Power consumption across the plant is closely monitored and managed. Many Honda facilities are partially powered by solar arrays, wind energy, or cogeneration systems. Advanced lighting systems using motion sensors and LED technology ensure that energy is only used when and where it's needed. In some plants, Honda has achieved near-zero landfill status, meaning almost all waste materials, plastic, metal, rubber, even food waste, are recycled or repurposed in some way. Inside the modern Honda manufacturing plant, what might seem like a chaotic tangle of machines, parts, conveyors, and workers is in fact a precisely engineered environment orchestrated with clockwork efficiency. At this stage of production, where physical assembly transitions into post-production optimization and system refinement, the focus increasingly shifts from brute force manufacturing to intelligent systems management, what Honda refers to internally as manufacturing excellence. At the heart of this excellence is automation, an ever-present, evolving backbone of the modern Civic factory. Over 60% of tasks on the assembly line are now completed or assisted by robots. These are not simple, one-purpose mechanical arms, but intelligent, adaptable systems equipped with high-resolution sensors, 3D cameras, and real-time process feedback. In the body shop, robotic welders do far more than spot weld. They monitor the pressure of each weld in milliseconds, analyze the depth of each fusion, and dynamically adjust parameters to compensate for slight variations in steel thickness or surface contaminants. These adjustments happen in real time, with hundreds of data points captured per second and logged directly into Honda's centralized manufacturing database. Each of these robots is not just a tool, but a node in a larger intelligent network. That network, Honda's digital production control system, is built to track every Civic as it moves through the plant. From the moment a steel blank enters the stamping press to the final torque applied to the last wheel nut, the vehicle's identity is logged and linked to a database of component specifications, supplier batch numbers, sensor readings, machine parameters, and quality checks. This system allows Honda to maintain traceability, a key principle in modern automotive manufacturing. If a defect is ever found in a Civic's transmission casing or infotainment unit, engineers can instantly trace that part back to the day, time, and exact supplier lot it came from. This level of insight allows for surgical product recalls rather than sweeping generalizations, and is a cornerstone of Honda's commitment to quality and customer safety. In many zones of the factory, cobots or collaborative robots are replacing traditional industrial arms. These are smaller, more agile machines designed to work side by side with human operators. Unlike traditional robots that are fenced off behind safety barriers, cobots use proximity sensors, pressure feedback, and vision systems to detect the presence of humans and respond accordingly. For instance, in the trim assembly zone, cobots might assist a technician by precisely positioning heavy dashboard modules while the human secures them in place with fasteners. This reduces operator fatigue and improves assembly consistency, particularly for ergonomically challenging tasks that are difficult to automate entirely. Even AGVs, or automated guided vehicles, have seen substantial evolution. No longer confined to fixed track systems, newer Honda plants use vision-guided or LiDAR-based AGVs that navigate the factory floor independently, rerouting in real time to avoid traffic congestion or bottlenecks. These intelligent carts move everything from seats and dashboards to windshield glass and wiring harnesses, all without human input. Each AGV is linked wirelessly to the central factory control hub, which orchestrates their movements in relation to production flow. They are programmed to deliver specific components to a station at a precise time, synchronized with the exact Civic model being assembled at that moment. And this synchronization is not theoretical. Honda employs a modular assembly system, meaning that various trim levels, powertrain variants, and color options are built on the same line, back to back, without downtime. A Civic Sport with manual transmission might be followed directly by a Civic Touring with a CVT and an entirely different dashboard layout. Each workstation is equipped with smart tools, torque wrenches that automatically adjust to the specification required for that trim, vision systems that verify part fitment, and pick-to-light component bins that illuminate only the exact part required for that vehicle configuration. The system dynamically adapts the line to each unique build without requiring tool changes or reprogramming. In areas such as windshield installation or seat alignment, machine vision systems play a critical role. High-definition cameras capture detailed images of each step in the process, comparing live data to reference models stored in the system. These cameras can detect misalignments as small as 0.2 millimeters and instantly alert workers or trigger robotic correction. If a deviation is beyond correction thresholds, the system flags the vehicle and diverts it to a diagnostic bay for human evaluation. These inline quality checks are far more than visual. They're statistical safeguards, using large data samples to spot trends before they become problems. The paint shop, often one of the most energy-intensive parts of the plant, has also embraced advanced automation. Honda's robots not only apply base coats and clear coats with micron-level consistency, they also self-monitor the viscosity of paint, adjust spray patterns for optimal atomization, and even self-clean their nozzles between cycles. Overspray, which historically represented significant waste, is now captured by electrostatic plates and returned to a closed-loop reclaim system. Humidity and airflow in the paint booths are adjusted in real time to compensate for changes in ambient conditions, ensuring flawless finish consistency across seasons and global regions. Underpinning all of this automation is a layer of predictive analytics. Honda doesn't just react to faults, it forecasts them. Every sensor, robot, conveyor, and torque gun in the plant feeds data into a centralized AI-driven platform that looks for anomalies. If a certain fastener is being torqued more tightly than normal over a series of builds, the system flags the deviation. It may indicate tool wear, part misfit, or an upstream supplier issue. Engineers are alerted before a failure occurs. This predictive maintenance approach has dramatically reduced downtime and improved first-pass yield, an industry metric referring to the percentage of vehicles that pass inspection without needing rework. In the engine assembly hall, torque sensors are so precise they can detect if a technician has even one thread of a bolt cross-threaded. If detected, the system locks the build station, highlights the error on a display, and prevents the engine from moving forward until the issue is addressed. These safeguards ensure that even as production volume increases, Honda maintains the reliability and consistency that the Civic name is built upon. Lighting across the factory is controlled by intelligent energy management systems. LED lights adjust brightness based on time of day, production activity, and occupancy, cutting power usage dramatically. Heating and cooling systems adapt to the number of people in a zone and the thermal load of nearby machines. Even compressed air systems used in pneumatic tools and robotic actuators are monitored for leaks. Any pressure drop triggers an alert and isolates the zone for maintenance. These efficiencies not only reduce environmental impact, but also contribute to cost savings that allow Honda to reinvest in manufacturing innovation. As Civic production continues around the clock, every process, every station, and every worker is part of a living, learning system. The factory itself becomes smarter with time. Lessons learned from one batch of Civics are automatically integrated into subsequent runs. And when a mid-cycle refresh or new feature is introduced, say a redesigned infotainment interface or new powertrain calibration, the change is implemented digitally across the plant. Robots are updated wirelessly with new motion paths. Technicians receive augmented reality instructions via tablet. Part suppliers are given revised sequencing instructions within minutes. As the Honda Civic continues its evolution on the global stage, one aspect of its production has grown increasingly central to the company's mission: sustainability. Manufacturing a modern automobile like the Civic requires immense amounts of energy, materials, water, and logistics, all of which must now be managed under the pressure of carbon emissions reduction and environmental stewardship. Honda's response to this challenge has been far from superficial. In many ways, its Civic production lines have become test beds for the company's broader efforts in building low-impact, resource-efficient factories. Every modern Civic plant is built with environmental performance targets baked into its architecture. From the outset, Honda employs what it calls Green Factory Principles, a framework of metrics and strategies for reducing energy consumption, carbon footprint, chemical emissions, and waste. These principles are applied at every level, from site selection to machinery operation. One of the most visible aspects of this sustainability initiative is Honda's aggressive use of renewable energy sources. Several Civic production plants, such as the one in Greensburg, Indiana, use large-scale solar panel arrays to offset electricity usage. These panels are often installed on the roofs of buildings or in dedicated solar fields adjacent to the facility. While they may not yet power the entire operation, they significantly reduce reliance on fossil fuels and provide a stable energy source for specific systems like lighting grids or HVAC. In addition, some facilities make use of combined heat and power systems, also known as cogeneration units, which burn natural gas to generate electricity on-site while capturing waste heat to provide hot water and climate control. These systems can be more than twice as efficient as pulling electricity from the grid alone, significantly cutting greenhouse gas emissions per kilowatt hour used. But it isn't just energy that's optimized. Water usage is a critical sustainability issue, particularly in the paint shop, where thousands of liters are required daily for rinsing, cleaning, and chemical mixing. Honda's solution has been the implementation of closed-loop water recycling systems. These systems use a mix of ultrafiltration membranes, reverse osmosis, and UV sterilization to clean and recirculate water through the plant. In some factories, as much as 95% of water used in production is reclaimed and reused. The E-Coat dip tanks, for example, are now topped off with recycled water that meets near laboratory-grade purity standards. Chemical usage in painting and metal treatment processes has also been re-engineered. Honda has transitioned many of its surface preparation and cleaning solutions to low VOC and phosphate-free alternatives. This not only reduces hazardous waste, but also improves worker safety and air quality inside the factory. Ventilation systems are fitted with electrostatic scrubbers and HEPA filters to capture overspray particles and solvent vapors, reducing emissions that would otherwise enter the atmosphere. Solid waste is handled with equal intensity. Modern Honda Civic plants operate on a near zero landfill policy. That means virtually all manufacturing waste, scrap metal, plastics, rejected parts, packaging materials, even cafeteria waste, is sorted, recycled, or repurposed. Steel offcuts from the stamping shop, for instance, are collected automatically by magnetic conveyors and baled for return to the steel mill. Plastic injection molding runners are ground up on site and reintegrated into new parts. Waste lubricants are filtered and reused for non-critical applications. To track the progress of these initiatives, every plant maintains a real-time environmental dashboard, visible to both operators and management. This dashboard displays metrics like kilowatt hours per car produced, liters of water used per cycle, paint shop VOC emissions, and recycling rates. Engineers use this data to identify inefficiencies and launch Kaizen initiatives, small, continuous improvements that ripple across departments and compound over time. These dashboards are also shared across Honda's global factory network to spread best practices from one facility to another. That global network is itself a masterclass in distributed manufacturing. Unlike some automakers that rely on a single central plant for specific models, Honda's Civic production is distributed across multiple countries. This includes facilities in Japan, the United States, Canada, the United Kingdom, Thailand, and others depending on generation and market. Each of these plants is capable of localized production, a practice where the Civic is manufactured with regional suppliers, regulations, and consumer preferences in mind. For instance, Civics built for the North American market may feature different safety systems, infotainment options, or climate control calibrations than those produced for Southeast Asia or Europe. This localization reduces the carbon footprint of global shipping, lowers costs, and allows Honda to respond quickly to local demand. Supporting this decentralized system is a globally synchronized digital architecture. Through Honda's global production operations system, every plant can access standardized blueprints, torque specs, quality benchmarks, and real-time engineering updates. If a supplier in Thailand discovers a defect trend in a batch of brake calipers, that information is immediately shared across the entire network, triggering preemptive inspections in other factories and supplier audits if necessary. It's a powerful example of how data is now just as important as steel in car manufacturing. These global factories are also adapting to accommodate a rising wave of powertrain diversification. As demand for cleaner transportation grows, Honda has committed to electrification, not just in full EVs, but also in hybrid and plug-in hybrid variants. For the Civic line, this means that certain factories now have dual powertrain capability, allowing them to produce both internal combustion and hybrid electric Civics on the same line. This feat of integration requires major adjustments to logistics, assembly sequencing, and training. Hybrid Civics require the installation of battery packs, inverters, high voltage wiring, and regenerative braking systems, all components absent in a traditional Civic. These parts arrive from Honda's dedicated eDrive suppliers, or in-house battery module assembly units. Once in the plant, they are carefully synchronized with the hybrid vehicle builds using the same just-in-sequence delivery system used for conventional components. Specialized battery handling equipment is required to safely transport and install the high-voltage packs, which are typically mounted beneath the rear seat or trunk floor. Technicians working in these zones receive additional safety training and wear insulated gloves, tools, and personal protective equipment. The factory floor is also reconfigured to include voltage-safe testing bays, where hybrid Civics undergo electrical system calibration, battery charge verification, and inverter diagnostics before leaving the plant. Furthermore, Honda is increasingly experimenting with modular EV production cells, small, independently operable lines dedicated to electric vehicle production. While not yet widespread for Civic manufacturing, these modular cells are being piloted as scalable units that can be added to existing facilities as EV demand grows. Their flexible footprint and self-contained operation allow them to be spun up quickly in response to market shifts. There's also a growing presence of simulation-driven design in the manufacturing pipeline. Before a new Civic variant ever hits the factory floor, it is built virtually inside a high-resolution, physics-accurate 3D model of the plant. Engineers can simulate every weld, fitment, fastener torque, and wiring route before any physical part is produced. These simulations help identify potential interference issues, ergonomic challenges, or inefficiencies long before they reach real workers or robots. The result is faster model ramp-up, fewer line stoppages, and improved first-time quality. Even the training of plant staff is evolving. New workers learn procedures not just from manuals or trainers, but through augmented reality overlays that guide them step by step. Wearing AR glasses or using tablets, they can see animated instructions projected onto real parts, highlighting the correct bolt, identifying the right clip location, or warning about torque sequence. This immersive training dramatically shortens the learning curve and reduces mistakes. Through all of these innovations, sustainable processes, global synchronization, powertrain diversification, and smart manufacturing technologies, the Honda Civic continues to set the standard for what a mass-market, high-efficiency automobile production line can achieve. And it does so not with gimmicks or short-term fixes, but with systems thinking, scientific rigor, and decades of accumulated expertise. The journey starts as a concept long before steel meets the press or engines meet the chassis. Engineers and designers spend months, sometimes years, refining the blueprint of a model. Every curve of the bodywork, every mechanical component, and every safety feature is planned with meticulous care. It is not simply about designing something that looks appealing, but ensuring that every component can be manufactured reliably, assembled efficiently, and maintained for years of use. When the design is finalized, the preparation for production shifts into the realm of manufacturing engineering. This is where the physical requirements for building the car are translated into a sequence of processes, machines, and assembly operations. The factory layout is adjusted to accommodate new tooling and equipment. The stamping presses, welding robots, painting lines, and assembly stations are prepared in harmony, ensuring that the entire flow of production can move like a well-orchestrated symphony. Each department communicates with the others to align their timing, capacity, and technical requirements, because any mismatch between stages can create bottlenecks that slow the entire plant. Before we even see the first car body taking shape, we must understand the raw materials that feed this system. The backbone of every Suzuki vehicle is steel, but not just any steel. High-strength automotive steel sheets arrive from steel mills in giant coils, sometimes weighing over 20 tons each. These coils are delivered by rail or truck to the factory's stamping plant. Alongside steel, aluminum panels, plastics, resins, and a variety of other materials are delivered in a steady flow. The supply chain for a car factory is an ongoing pulse of incoming goods, timed precisely so that inventory storage is minimized. Many parts and sub-assemblies come from a network of suppliers that specialize in producing components such as seats, dashboards, headlights, and braking systems. Some of these suppliers operate right next door to the Suzuki plant in what is known as a supplier park to enable just-in-time delivery directly to the assembly line. The steel coils, once unloaded, are stored for only a short period before being moved to the stamping department. This is the first truly transformative stage of car manufacturing. In a cavernous hall filled with the rhythmic thunder of stamping presses, the steel sheets are uncoiled, flattened, and fed into enormous press machines. These presses exert thousands of tons of force, shaping the steel into the contours of fenders, doors, hoods, and roof panels. Each press operation uses dies, massive, precisely machined blocks of steel that mold the sheet metal into exact shapes. The dies can weigh several tons and are swapped out when changing to a different panel design. A single car body panel often requires several stages of pressing, beginning with a rough form in the first die, followed by progressively more refined shapes in subsequent dies, until the panel meets its exact specifications. During stamping, every millimeter matters. Automated optical inspection systems check the freshly pressed panels for surface defects, ripples, or dimensional deviations. Any panel that does not meet standards is set aside for recycling, its metal returned to the melting process to be reformed into new sheets. This reduces waste and ensures that only flawless panels proceed to the next stage. The next stop for these panels is the body shop, an enormous section of the plant where the raw pressed steel pieces come together to form the recognizable skeleton of a Suzuki car. Here, the air is filled with the bright sparks of robotic welding arms. The panels are loaded into large jigs and fixtures that hold them in precise alignment while robots perform spot welds. These welds fuse the panels together permanently, ensuring structural rigidity and safety. For a modern Suzuki, this stage is heavily automated, with banks of robots working in perfect synchrony. However, skilled human operators remain essential for overseeing the process, making adjustments, and performing welds in tight or complex areas where robots cannot easily reach. The construction of the car body, known as the body in white, follows a carefully choreographed sequence. The floor pan, which forms the base of the vehicle, is placed first. Side panels and door frames are aligned and welded onto it, followed by the roof, front, and rear sections. Cross members, reinforcements, and brackets are added in specific places to enhance crash protection and structural strength. Door openings are checked against strict dimensional tolerances to ensure that later, when doors are hung and adjusted, they will fit perfectly without rattling or misalignment. At various points in this body shop process, quality control engineers measure critical points on the structure using laser scanners and coordinate measuring machines. This prevents small errors from compounding into serious alignment issues later. The body in white, once fully welded, is a bare shell of gleaming steel. It has no paint, no trim, no glass, but its proportions and integrity are set for the rest of its life. Before painting, the bare metal body must be prepared meticulously. Even tiny traces of oil from stamping or dust from welding can cause paint defects. Therefore, the bodies are sent through a cleaning and pre-treatment line. They are dipped in a series of chemical baths that remove contaminants, apply a phosphate coating to improve corrosion resistance, and prepare the surface for paint adhesion. This pre-treatment line is fully enclosed, and the bodies are moved on an overhead conveyor through each tank, sometimes fully submerged, to ensure every crevice is treated. The final step in this stage is a drying oven that removes all moisture. Only then does the car proceed to the paint shop, a section of the factory that feels completely different from the noisy stamping or welding halls. Here, the environment is controlled for temperature, humidity, and cleanliness. Dust particles are the enemy of smooth automotive finishes, so the entire paint area operates with filtered air and positive pressure to keep contaminants out. The first layer to be applied is the electrophoretic primer, also called E-coat. The car body is immersed in a bath where an electric current causes primer particles to bond evenly to every surface, inside and out, including hard-to-reach cavities. Once the primer is cured in an oven, sanding robots and human operators smooth the surface before the application of the base coat, which provides the car's color. Depending on the model, Suzuki may use robotic spray arms that follow precise patterns to ensure even coverage, especially around edges and curves. After the base coat, a clear coat is applied to provide gloss and protect the color from ultraviolet damage and environmental wear. Each coat is baked at controlled temperatures to ensure hardness and adhesion. As the painted shells emerge from the curing ovens, they are inspected under powerful lighting in what is often called the light tunnel. This is a controlled environment where every curve of the car's surface is scrutinized by trained eyes and optical sensors for even the smallest imperfection. A speck of dust caught under clear coat, a ripple in the finish, or an uneven tone in the paint can be enough for a vehicle to be sent back for refinishing. In automotive manufacturing, these cosmetic checks are not mere vanity. They are essential to meeting customer expectations and protecting the long-term integrity of the finish. Only after passing these surface quality tests does the body proceed to what is known as the trim line. The trim line is the first phase where the car begins to be filled with the parts that make it functional and comfortable for passengers. The process is meticulously sequenced. Every car moving down the line has a build specification loaded into the plant's production system. This ensures that the correct color interior, optional features, wiring configurations, and mechanical components are installed at exactly the right point. Workers and automated equipment access the build information via monitors or handheld devices so there is no guesswork about which parts to install. The first installations are typically sound deadening materials. Large sheets of insulating mat are fitted to the floor, inside the doors, and sometimes behind interior panels to reduce road and engine noise. Wiring harnesses are then routed through the body. These harnesses are pre-assembled bundles of wires that carry electrical signals to lights, sensors, power windows, and entertainment systems. Fitting them correctly is critical. Any pinched wire or poor connection can lead to costly troubleshooting later. Harnesses are secured with clips and ties to prevent movement or abrasion over years of use. While the wiring is being routed, HVAC ductwork is fitted, ensuring that heating and cooling air can reach every vent in the cabin. This is followed by the dashboard assembly, which is often delivered as a complete unit from a supplier. Installing a dashboard is a delicate maneuver, as it must align perfectly with mounting points while accommodating wiring connectors, instrument clusters, and control modules. A team of technicians guides it into place and secures it with fasteners that have specific torque requirements to avoid rattles or stress on the materials. Seats are another major interior installation. These arrive pre-assembled, complete with upholstery, cushioning, and any built-in electronics such as seat heaters or airbag modules. Using mechanical assists to avoid strain, workers position the seats in the cabin and bolt them to the floor mounts. Seat positioning is not only about comfort. It has to align with seatbelt anchor points and airbag deployment geometry for safety. Parallel to interior fitting, work begins on marrying the body to the mechanical heart of the car, the chassis, and drivetrain. This is a carefully timed coordination between two moving lines, one carrying the prepared body shells and another carrying the assembled underbody module, which includes the engine, transmission, suspension, exhaust system, and braking components. The underbody is prepared in a separate section of the plant, often referred to as the chassis line, where technicians and robots assemble the engine and transmission onto a subframe, attach the front and rear suspension assemblies, mount the exhaust system, and connect steering linkages. In the case of Suzuki's smaller passenger vehicles, these assemblies are designed to be compact yet easy to service, with many components integrated into modular subframes. This not only speeds up initial assembly, but also allows for easier maintenance during the vehicle's lifetime. The wheels and tires are sometimes fitted at this stage, though final torque on wheel nuts may be left until later in the process to account for transport considerations within the factory. The moment known as the marriage is one of the most striking in car assembly. The painted body shell is lifted slightly above the moving chassis assembly by a synchronized hoist system. As the chassis slides into position beneath the body, the two are lowered together, and a team quickly secures them with precision fasteners. At this point, the car's major structural integration is complete. The engine and drivetrain are physically connected to the body. Once married, the vehicle moves to stations where cooling lines, fuel lines, and electrical connections between the body and chassis are linked. This requires careful attention to routing, sealing, and securing. Every hose clamp, connector, and grommet is placed to avoid chafing or leaks, as even a small oversight here could lead to operational failures after delivery. The next focus is glazing, the installation of windows and windshields. Modern automotive glass is bonded to the body using high-strength urethane adhesives, which not only hold the glass in place, but also contribute to the vehicle's structural rigidity and crash performance. Before installation, the glass edges are treated for adhesion, and the body's window frames are cleaned and primed. Robotic applicators or skilled technicians lay a precise bead of adhesive, and the glass is positioned using vacuum lifters to avoid direct handling. Proper curing of this adhesive is critical. and vehicles are timed through the assembly process so that the bond sets before the car experiences any structural flex. After the glass is fitted, exterior trim pieces are added. These can include weather strips, side moldings, roof rails, and badging. The fit and finish of these components are critical to the car's perceived quality. Misaligned trim can create wind noise or water ingress, while inconsistent badging undermines visual symmetry. The doors, which may have been removed earlier for easier access during interior work, are now reattached. They are hung on hinges that allow for fine adjustment, ensuring consistent panel gaps and smooth operation. Once aligned, the doors receive their inner panels, window regulators, locks, and wiring for power accessories. The tailgate or trunk lid undergoes a similar process, with alignment checked to within millimeter tolerances. As the car progresses down the line, more systems come online. Fluids are filled: engine oil, transmission fluid, coolant, brake fluid, power steering fluid, and windshield washer solution. In many plants, these filling systems are automated to ensure precise volumes and to reduce spillage. The first electrical power-up occurs at this stage, allowing the vehicle's onboard computer systems to initialize. This is the moment where workers can begin testing electrical functions like lighting, wipers, and infotainment displays. Once the newly assembled Suzuki approaches the end of the main assembly conveyor, the atmosphere in the plant shifts from a building process to one of verification and fine-tuning. This is the beginning of the commissioning stage, where the focus moves from installing components to ensuring that everything functions exactly as intended. The car is no longer just a collection of parts. It is a complete vehicle that must now prove itself ready for the road. The first stop after major assembly is often the wheel alignment station. Here, the vehicle is placed on a set of precision plates and laser-guided measurement systems that check the angle of each wheel relative to the chassis and to one another. Proper alignment is critical for handling stability, tire wear, and driver safety. Adjustments are made using specialized tools that tweak the suspension's camber, caster, and toe settings until the readings fall within strict tolerances defined by Suzuki's engineering specifications. This step also ensures that the steering wheel will be centered when the car is driven in a straight line, preventing an issue that would be instantly noticed by a new owner. Following alignment, the car moves to the fluid check and topping station. Although fluids have already been added during earlier stages, they are now checked for correct levels and quality. Any air bubbles in hydraulic systems, such as the brakes or clutch, are purged through a process known as bleeding, ensuring consistent performance. Coolant systems are pressure tested to confirm there are no leaks, and the fuel system is primed and checked for tightness to avoid vapor or liquid escapes. Each of these checks is both a safety measure and a warranty safeguard, as fluid leaks can lead to early vehicle failures. Now comes one of the most anticipated moments in the factory: the first engine start. At a dedicated station, the technician inserts the ignition key or engages the start button, bringing the Suzuki's engine to life for the first time. This is not a ceremonial step, but a critical diagnostic event. As the engine runs, technicians listen for abnormal sounds, check for warning lights on the instrument cluster, and monitor the readouts from diagnostic equipment connected to the vehicle's onboard computer. The engine control unit records any fault codes during the first start, and these must be addressed immediately before the car can progress. This step also ensures that fuel delivery, ignition timing, idle control, and emission systems are functioning properly from the outset. Once the initial engine check is complete, the car enters what is called the rolling road test. This is essentially a dynamometer station built into the assembly line. The vehicle is driven onto large rollers, which allow the wheels to spin as though the car were traveling down an actual road. The technician operates the vehicle through various speeds and loads, while sensors measure engine output, drivetrain smoothness, and braking performance. Onboard equipment also checks that gear shifts are smooth in both manual and automatic transmissions, that traction control engages correctly, and that the ABS activates as designed during simulated stops. For hybrid or electric Suzuki models, the rolling road test verifies battery performance and regenerative braking operation as well. After this dynamic evaluation, the car undergoes an emissions test. The exhaust gases are captured in a sealed system connected to high-precision analyzers that measure the concentration of pollutants such as carbon monoxide, hydrocarbons, and nitrogen oxides. The results must comply with the regulations of the market where the vehicle will be sold. If any parameter is out of range, adjustments to the engine management software or mechanical repairs are made immediately. Emissions compliance is one of the most heavily regulated aspects of vehicle production, and no car can leave the factory without passing this check. With the mechanical and electronic systems validated, attention turns to the finishing area. This is where skilled technicians examine the entire vehicle for fit and finish issues. The car is inspected under bright lighting and from multiple angles to detect paint blemishes, uneven panel gaps, or imperfections in trim alignment. Special gauges are sometimes used to measure panel gaps to within fractions of a millimeter, ensuring consistency from one vehicle to the next. In addition to visual checks, technicians test all customer-facing features. Every switch, button, knob, and lever is operated to confirm proper function. Windows are raised and lowered, mirrors adjusted, wipers cycled, and climate control systems run through heating and cooling modes. Infotainment systems are powered up to verify screen clarity, touch sensitivity, and speaker output. Even less obvious features, like seat height adjusters and child safety locks, are tested to avoid customer dissatisfaction. The underbody of the car is also inspected at this stage, typically with the vehicle lifted on a hoist. Inspectors look for fluid leaks, loose fasteners, or improperly routed cables and hoses. Protective coatings applied to resist corrosion are checked for completeness, especially around weld seams and in wheel wells where road spray is most intense. Once all systems are confirmed, the car enters the water test booth. This is an enclosed chamber equipped with high-pressure spray nozzles that douse the vehicle from every direction for several minutes, simulating heavy rainfall and splash conditions. After the soaking, technicians climb inside to check for any water ingress around doors, windows, or the trunk area. Sealing defects are corrected immediately, as water intrusion can lead to electrical failures and interior damage over time. If the car passes all these stages, it proceeds to the final audit line. This is often staffed by some of the most experienced personnel in the factory, as they perform a comprehensive review of the vehicle. The final audit is essentially a condensed version of all earlier checks combined into a single process. It includes visual inspection, functional testing, and a short, low-speed road test within the plant grounds. Any fault, no matter how minor, is documented and corrected before the car can be released. Once signed off, the vehicle's identification and tracking information in the production database are updated to reflect that it has cleared manufacturing. Protective coverings are then applied to vulnerable areas like the hood, roof, and interior surfaces to prevent damage during transport. From here, the Suzuki moves into the dispatch yard where cars are grouped according to their destination markets. Some are loaded onto specialized car transport trucks, while others are driven onto railway wagons designed for vehicle shipment. For export markets, vehicles are often taken to a port facility where they are driven into large car carriers, ocean-going ships with multiple decks capable of holding thousands of cars. Throughout this entire process, Suzuki's production philosophy emphasizes continuous improvement. Every issue found during assembly or final inspection is logged in a central system. allowing engineering and quality teams to analyze trends and implement corrective measures. This feedback loop ensures that problems are addressed at their source rather than repeatedly corrected downstream. Once a Suzuki car has passed its final factory inspection and been fitted with protective coverings, its story shifts from manufacturing to logistics. This is a crucial and often underappreciated stage because even the most perfectly built vehicle must arrive at its final destination without damage, delay, or compliance issues. The dispatch yard of a Suzuki plant operates with the same precision as the assembly line itself, ensuring that each vehicle is correctly identified, grouped, and routed toward the market it is intended for. Vehicles are scanned into a tracking system using their vehicle identification number, or VIN, which serves as a unique fingerprint for each car. The VIN is tied to the car's exact configuration, model, trim level, color, engine type, and any special market-specific features. This tracking system communicates directly with Suzuki's global distribution network, allowing logistics planners to match production output to regional demand forecasts. The cars are arranged in neat rows within the yard, typically grouped by destination, so that loading can be performed efficiently. For domestic markets, the vehicles are usually transported by specialized car carrier trucks. These trucks are designed with hydraulic ramps that can be adjusted to accommodate multiple rows of vehicles, often up to 8 or 9 depending on size. Drivers are trained in securing the cars with wheel straps or chocks to prevent movement during transit. The loading sequence is carefully planned so that the first vehicles to be delivered are loaded last, minimizing handling at intermediate stops. For longer distances within the same country, rail transport is sometimes preferred. Trains can carry hundreds of vehicles in enclosed rail cars, protecting them from weather and debris. The loading process involves carefully driving each Suzuki up narrow ramps and into the railcar bays, with only centimeters of clearance on each side. Drivers in this operation are trained to maintain extremely slow, steady movement to avoid any accidental scrapes. The railcars are then sealed until they reach the unloading terminal, often located near major distribution centers. When cars are destined for international markets, the process becomes more complex. Export-bound Suzukis are loaded onto massive ocean-going vessels known as roll-on/roll-off ships, or RoRos. These ships function like floating parking garages, with multiple decks connected by internal ramps. Vehicles are driven aboard under their own power and parked in tight formation, with only enough space for mirrors and doors to avoid contact. Crews secure each car with wheel chocks and lashings to keep them stable during the voyage. Depending on the route, these ships can carry thousands of vehicles at once, stopping at several ports before reaching their final destinations. The voyage can last anywhere from a few days to several weeks, depending on the distance between the plant and the destination port. During this time, the vehicles remain sealed and untouched with their protective films and coverings intact. Because environmental conditions at sea can vary, including salt-laden air, the factory-applied coatings and transport wraps are specifically chosen to prevent corrosion or cosmetic damage. Once the ship reaches its destination port, a highly coordinated unloading operation begins. Teams of trained port drivers board the ship and drive the cars off in a continuous flow, following a pre-planned sequence. The cars are then parked in secure port storage yards, where customs clearance procedures are initiated. Every country has its own import regulations, and Suzuki's logistics team ensures that each vehicle's documentation, including emission certificates, safety compliance paperwork, and shipping manifests, is complete and accurate before customs inspection. After clearing customs, the vehicles are typically sent to a regional distribution center. Here, a process called pre-delivery inspection, or PDI, takes place. Although the car has already been tested extensively at the factory, the PDI ensures that nothing has changed during transport. Trained technicians remove protective coverings, inspect the bodywork for any transit-related damage, check all fluid levels, and verify that the battery is fully charged. Tires are inspected for correct pressure, and software updates may be installed if newer calibration files have been released since the car left the factory. This is also where market-specific adjustments are made. For example, vehicles shipped to countries with different lighting regulations might have headlight aim adjusted or daytime running lights enabled or disabled according to local laws. Navigation systems are loaded with the correct regional maps, and owner's manuals in the appropriate language are placed in the glove compartment. If a dealer has ordered optional accessories such as roof racks, spoilers, or upgraded infotainment units, these may be installed at the distribution center to avoid slowing down the main assembly line. Once PDI is complete, the cars are released for final transport to dealerships. Depending on geography, this may involve another short truck journey or additional rail transit. Dealers receive advance notice of incoming stock through Suzuki's dealer management system, allowing them to prepare showroom space and schedule customer handovers for pre-sold vehicles. When the cars arrive at the dealership, the process takes on a more personal dimension. Dealership staff conduct their own incoming inspection to confirm that the car is in perfect condition. Any final detailing, such as washing, waxing, or vacuuming, is performed to ensure a showroom-ready presentation. Paper floor mats, seat covers, and steering wheel protectors are removed, revealing the untouched interior. If the vehicle is destined for immediate delivery to a customer, the dealership staff will carry out the handover procedure. This involves explaining the car's features, demonstrating controls, and answering any questions the customer might have about operation or maintenance. The VIN is registered in the dealership system along with the customer's details, marking the official start of the warranty period. From the customer's perspective, the journey begins the moment they take the keys. From the factory's perspective, however, the cycle never truly ends. Feedback from dealerships about customer experiences, warranty claims, and any recurring issues flows back to Suzuki's engineering and manufacturing teams. This closed-loop communication helps identify opportunities for product improvements, process refinements, and supplier quality enhancements. Interestingly, the logistics chain is also part of Suzuki's environmental strategy. Modern vehicle transport planning aims to minimize unnecessary mileage and fuel use, sometimes even consolidating shipments from multiple manufacturers onto the same vessel or rail line to reduce emissions. In some markets, Suzuki works with dealerships to arrange bulk deliveries that reduce the number of trips and associated carbon footprint. In global terms, the distribution network is as critical to Suzuki's reputation as the production line itself. A flawless manufacturing process can be undermined by mishandled shipping, customs delays, or damage in transit. This is why Suzuki invests heavily in both technology and training to ensure that from the moment a vehicle leaves the assembly line until it arrives in the customer's driveway, it remains in the same pristine condition it was in at the final factory inspection. While the sight of finished Suzuki vehicles streaming out of the plant toward dealers and customers is the most visible sign of success, the real heartbeat of the company's manufacturing prowess lies in what happens behind the scenes. The precision of assembly, the timing of parts deliveries, and the consistency of quality all trace back to an intricate web of engineering coordination, supply chain management, and production system design. This interconnected system is what allows Suzuki to produce vehicles in large volumes without sacrificing the meticulous detail that defines a well-made car. The cycle begins long before the first sheet of steel is pressed, with engineering teams designing every component to be not only functional but manufacturable. This is known as design for manufacturability, or DFM. The aim is to ensure that parts can be produced consistently at the right tolerances and installed efficiently on the assembly line. For instance, a bracket might be designed with built-in alignment features that allow it to snap into place in only one orientation, eliminating the possibility of incorrect installation. Even the routing of a wiring harness is planned to minimize the number of bends and attachment points, reducing both assembly time and the risk of damage. This level of planning requires intense collaboration between product design engineers, manufacturing engineers, and even supplier representatives. Suppliers are involved early in the process to provide feedback on material selection, forming methods, and cost implications. A headlight supplier, for example, might work directly with Suzuki's styling team to adapt a design so that it can be assembled with fewer screws or clips, speeding up installation on the trim line. These interactions happen months, often years, before a model reaches production. Once the design is frozen, Suzuki's manufacturing engineers turn their attention to the factory itself. Every model introduction requires a detailed assessment of the production line layout, tooling, and automation requirements. This might involve installing new welding jigs for body panels, programming robots for different spray patterns in the paint shop, or creating custom assembly fixtures for unique components. Retooling a line is a massive undertaking, often done during scheduled downtime, to avoid disrupting ongoing production of existing models. One of the most critical decisions at this stage is determining the level of automation versus manual labor for each process. Suzuki, like many automakers, uses robots extensively for operations that demand absolute consistency, such as spot welding, seam sealing, and paint application. Robots excel at repetitive, high-precision tasks, and their ability to work in hazardous environments, like the fumes of a paint booth, improves worker safety. However, there are many tasks where human skill remains unmatched. Complex interior installations, final fit adjustments, and quality inspections often rely on trained technicians whose judgment and dexterity can adapt to small variations. For example, adjusting a door to achieve a perfect gap relative to the body involves subtle manipulation that a robot cannot yet match with the same flexibility. Suzuki's philosophy tends to blend automation with human oversight, creating hybrid workstations where robots perform the heavy lifting and humans ensure the final finesse. To keep everything running smoothly, Suzuki employs just-in-time manufacturing principles. This means parts arrive at the assembly line precisely when needed, rather than being stockpiled in large quantities. The benefit is reduced inventory costs and the ability to respond quickly to changes in demand. But this also requires a flawless supply chain, where every supplier delivers exactly on schedule. Any delay, whether from a parts plant, a transportation breakdown, or a customs holdup, can halt the entire assembly line within hours. To mitigate this, Suzuki maintains contingency plans and sometimes dual sources critical components so that production is less vulnerable to disruptions. The flow of materials within the factory is another area of intense engineering attention. Components are often delivered in sequenced racks, arranged in the exact order they will be installed. This eliminates the need for workers to search for the correct part, shaving seconds off each installation and reducing the risk of mistakes. In high-volume areas like the trim line, these seconds add up to major efficiency gains over the course of a day. Information flow is just as important as material flow. The entire production line is governed by a manufacturing execution system that tracks each vehicle in real time. As a body shell enters the assembly line, its VIN is scanned, and its build sheet is instantly displayed as improvements, no matter how small. A simple change in the shape of a parts bin or the angle of a work platform can reduce strain, prevent errors, or shave time from a process. These changes are documented, evaluated, and, if effective, standardized across the production line. quality control is embedded at every stage, not just at the end. Inline inspection stations use laser scanners, vision systems, and torque sensors to verify that parts are installed correctly and that critical dimensions are within tolerance. If a defect is found, the car can be diverted to an offline repair bay for immediate correction. This prevents issues from traveling further down the line where they would be more difficult and costly to fix. Equally important is the feedback loop between manufacturing and product engineering. When recurring assembly difficulties or component defects are identified, this information is relayed back to the design teams. They can then modify the design or manufacturing process to prevent the issue in future builds. For example, if a clip securing a wiring harness is found to be difficult to engage consistently, the design might be altered to make it more forgiving during installation. In essence, Suzuki's manufacturing ecosystem is a continuous conversation between design, production, and logistics. Each element shapes and supports the others, creating a tightly knit system capable of turning raw materials into road-ready cars at scale. It is this deep integration that allows Suzuki to maintain both cost efficiency and the reliability that customers expect. To understand how a Toyota car is made, one must first step into a space where discipline, precision, and respect for process define every movement, the Toyota factory. Within these facilities, the transformation from raw materials to a fully functional vehicle is not simply a mechanical progression, but a living manifestation of a philosophy. This philosophy, known globally as the Toyota Production System, or TPS, is centered on two foundational pillars: Jidoka, automation with a human touch, and just-in-time manufacturing. Together, these principles dictate how every Toyota vehicle is born. Imagine walking into one of Toyota's flagship plants, such as the Tsutsumi plant in Toyota City, Japan, or the Georgetown facility in Kentucky. The air is filled not with chaos, but with a quiet, rhythmic hum. It is not the sound of urgency, but of synchronization. Workers, robots, and machines operate in precise harmony, each step of the process unfolding like clockwork. Every bolt tightened, every part aligned, every inspection performed. Nothing is rushed, but nothing is delayed. The objective is not to build fast, but to build flawlessly, and in the smallest increment of time and resource necessary. The beginning of any Toyota vehicle starts far upstream, not in the plant itself, but in the raw material supply chain. Toyota sources high-strength steel, aluminum, plastics, semiconductors, glass, and countless other materials through a tightly managed supplier network. Each supplier is held to stringent quality and delivery standards. Deliveries arrive at the plant just in time, often within hours of their use. This lean inventory philosophy reduces waste and ensures that the factory remains agile, able to adapt to shifting demands or changes in vehicle variants without maintaining massive backstocks. Once materials arrive, the first physical steps in vehicle creation occur in the stamping shop. Here, massive coils of steel or aluminum are loaded into enormous stamping presses, machines that weigh hundreds of tons and exert enough force to shape thick metal in a single, clean motion. These presses are fitted with die sets, precision-engineered molds that stamp out individual body components like fenders, hoods, roofs, and doors. The dies are swapped out by automated systems within minutes, allowing the line to shift seamlessly between models with minimal downtime, a critical capability in a mixed model facility. The stamped panels are then transported, often via overhead conveyor systems or autonomous carts, to the welding shop, the domain of the body in white. Here, the core structure of the car takes shape. Robotic arms, fitted with weld guns and sensors, orchestrate a ballet of sparks. These machines are programmed with exacting specifications to apply spot welds at predefined intervals, securing body panels together into a rigid, cohesive structure. Human technicians oversee the process, performing inspections, handling complex geometries, and activating and-on systems, alert cords, should any defect be found. Toyota's concept of judoka is exemplified here. Each welding station is empowered to halt the entire line if a defect or misalignment is discovered. This is not seen as failure, but as a safeguard for quality. Rather than allow a potentially flawed product to progress, the issue is stopped at its source, analyzed, and resolved before production resumes. Workers are trained not just to follow instructions, but to improve the process. This continuous improvement culture, known as Kaizen, is deeply embedded in every team member, from entry-level assemblers to plant managers. Once the car body has been assembled and verified for dimensional accuracy using laser measuring systems, it proceeds to the paint shop, where it is cleaned, sealed, primed, and finally painted. Before any color is applied, the body is immersed in a series of baths for electrodeposition coating, a process that prevents corrosion by electrically bonding a primer to the metal surface. The body then moves through a drying oven before entering the color application booths. Inside the paint booths, robotic arms fitted with rotary atomizers apply successive layers of primer, base coat, and clear coat. Each coat is inspected under intense lighting and humidity-controlled conditions to ensure consistency and to prevent inclusions such as dust or overspray. Technicians perform visual inspections and touch tests, sometimes sanding and reapplying paint if surface imperfections are found. The body then enters a final curing oven, where it is baked at high temperatures to harden the paint finish. By now, the car's basic structure is complete and coated, but it still lacks its soul: the engine, drivetrain, electronics, and interior. These elements come together in the general assembly area, a zone that stretches across hundreds of meters and involves hundreds of interwoven processes. It is here that Toyota's just-in-time philosophy truly comes alive. Unlike traditional batch manufacturing, Toyota's production line is mixed model, meaning different car types and trims, even with different engines or drive systems, are produced on the same line in whatever sequence is dictated by real-time customer orders. To accommodate this, parts are delivered in sequence to the line. If the next car is a Corolla hybrid with a panoramic roof, the exact seat configuration, roof headliner, battery pack, and other components for that configuration arrive seconds before the car reaches the station where they'll be installed. One of the most critical events in the assembly process is known as the marriage, the point at which the painted body is lowered onto the pre-assembled chassis. The chassis includes the engine, transmission, suspension components, exhaust system, and drivetrain. These assemblies are built up in parallel lines and synchronized with the main body line so that both components arrive at the marriage station at precisely the same moment. As the body descends onto the chassis, guided by precision jigs and hydraulic lifts, technicians align mounting points and fasten critical bolts using torque-controlled tools. Every fastening operation is digitally logged and monitored. If a bolt is under or over-torqued, or if a tool slips, the system immediately alerts the operator. These digital confirmations ensure traceability and enable Toyota to maintain records for every car that leaves the factory, supporting future warranty claims, recalls, or quality assurance audits. After marriage, the car begins to take on its recognizable interior form. Dashboards are installed as single pre-assembled units, often produced by Tier 1 suppliers in nearby satellite facilities and delivered just in sequence. Seats, wiring harnesses, air conditioning modules, infotainment systems, and airbags are carefully installed in a series of tightly choreographed steps. Workers use a combination of hand tools, smart torque guns, and pick-to-light systems, which light up the exact part bins for each operation to ensure accuracy and speed. This process continues with the installation of glazing, lighting elements, bumpers, wheels, and various trim components. Every part is fitted under strict quality standards with gap alignment and surface flushness, checked visually and digitally using laser systems. During each step, workers remain empowered to pull the andon cord if they detect an anomaly, reinforcing Toyota's belief that quality is built in, not inspected in. Once the assembly is complete, the vehicle is no longer a shell or a skeleton. It is a living machine, but one that has not yet been proven. The next phase will test every system, calibrate every sensor, and ensure that the Toyota badge on the front carries with it the weight of reliability, safety, and trust. Following the completion of physical assembly, each Toyota vehicle enters one of the most critical phases of the production lifecycle, the inspection, calibration, and functional testing stage. This is where mechanical craftsmanship meets analytical scrutiny. Every car must now prove that it not only fits together correctly, but that every system operates as designed, with the precision and reliability Toyota is globally known for. The first area the vehicle enters is typically the initial quality gate. Here, a multi-point check is performed by trained inspectors who methodically examine structural components, body alignment, and basic mechanical fitment. Every door, trunk, and hood is opened and closed to assess alignment and sound. Uneven gaps, misaligned panels, or abnormal resistance are noted and corrected on the spot. Workers use gap gauges, flushness sensors, and manual inspection tools to detect even the smallest deviations in build quality. From there, the vehicle proceeds to dynamic system checks. This is where the car begins to come to life, electronically and mechanically. A technician connects the vehicle to a factory diagnostic system, uploading the final software package to all electronic control units. In a modern Toyota, there can be 30 to 80 ECUs depending on the model, each managing a different subsystem, such as braking, power steering, stability control, hybrid drive, airbag systems, and infotainment. The ECUs are flashed with firmware specific to the car's trim level, engine type, and market destination. This step is highly sensitive, with redundant data verification systems to ensure the software uploads completely and correctly. Once configured, the system initiates a global self-check, where the vehicle essentially performs a diagnostic scan of itself. Each ECU confirms its functionality and readiness, while the technician monitors for error codes or inconsistent behavior. Any anomaly is logged and triggers a deviation procedure where the vehicle may be diverted to a separate diagnostics bay for deeper troubleshooting. Next, the car is transferred to a specialized station for fluid filling and pressure testing. Here, automated systems dispense exact volumes of engine oil, brake fluid, coolant, washer fluid, and, for hybrid or electric models, inverter coolant or battery thermal management fluids. These filling stations are digitally calibrated to prevent overfilling or contamination. During this stage, systems are also pressurized and sealed, then tested for leaks using pressure sensors and flow meters. Brake lines are tested by pressurizing the system and monitoring for pressure drops, ensuring every car leaves with a perfect, air-free hydraulic system. At this point, the vehicle is ready for its first engine start. A technician initiates ignition using either a key fob or the factory diagnostic console. The vehicle turns over and the engine comes to life. During this brief but critical startup phase, the system monitors RPM, oil pressure, exhaust sensor feedback, charging voltage, and other vitals. The technician listens for abnormal engine noise, checks idle quality, and watches for leaks or warning indicators. Once the engine stabilizes, the vehicle begins a series of automated or semi-automated functional tests, including shifting through gears, verifying steering assist, and checking basic throttle response. With the engine running and fluid circulating, The vehicle now moves to the dynamic test track or rolling road, depending on the facility's layout. On a rolling road, a stationary test bench with rotating drums. The car is accelerated through a simulated driving sequence. Braking, acceleration, shifting, emissions control, and hybrid transitions are all tested under load. This is where software calibration is fine-tuned. For example, hybrid systems may be evaluated for smooth transitions between electric and gasoline power, while adaptive cruise control sensors are calibrated to recognize distance targets. Meanwhile, headlight aim is adjusted using laser-guided alignment equipment. Wheel speed sensors are tested, and the vehicle's onboard safety systems, such as ABS and traction control, are confirmed to respond appropriately to artificial inputs. On some high-spec models, even the sound insulation is checked using internal microphones while simulating wind and road noise inside a soundproof chamber. Following dynamic testing, the car is driven to a water test booth, an enclosed chamber equipped with high-pressure nozzles, positioned to simulate heavy rain, splash conditions, and high-speed water exposure. The entire vehicle is blasted with water from above, below, and the sides. Technicians inside the booth, or using moisture detection tools afterward, check the interior for any signs of leakage, particularly around doors, glass seals, sunroofs, and underbody grommets. Vehicles that fail this test are sent to a specialized sealing team for inspection and repair before re-entering the final inspection queue. The penultimate step in the process is the final visual and tactile inspection line, often referred to as the white light tunnel. In this area, powerful overhead lights and side lighting replicate broad daylight, revealing surface imperfections invisible under factory lighting. Inspectors move around each vehicle slowly, checking for micro scratches, paint defects, misaligned trim, dirt under the clear coat, and material inconsistencies. The tactile elements are just as important: seat firmness, stitching alignment, trim tightness, and even the smoothness of control knob rotation are checked against factory benchmarks. Finally, once all systems are verified, paint and finish are pristine, and data records confirm the vehicle's complete build and performance history, the car is released from production. A digital certificate is issued, containing every measurement, torque value, fluid fill, software version, and test result from each phase of assembly. This data is stored in Toyota's secure manufacturing archive and is linked to the vehicle's VIN for life. If a component recall, software update, or warranty claim ever arises, this record becomes the reference point for diagnostic and corrective action. As a last step, protective films are applied to vulnerable surfaces like the hood, doors, and bumpers to prevent damage during transport. The vehicle is then driven to the shipping yard, where it is scanned, parked, and queued for delivery via truck, rail, or ship, depending on its final destination. The birth of a Honda automobile is not an accidental fusion of metal, glass, rubber, and electronics. It is the physical realization of a manufacturing philosophy rooted in discipline, simplicity, and human respect. At the core of Honda's automotive production process is the concept of monozukuri, a Japanese term meaning making things with craftsmanship and pride. For Honda, monozukuri is not just about building cars. It's about building trust in every nut and bolt, in every weld seam, in every panel gap. To witness a Honda car being built is to enter a tightly orchestrated environment where technological sophistication meets manual precision. Inside one of Honda's production facilities, such as the plant in Marysville, Ohio, or the Sayama factory in Japan, the scale is staggering. These plants are sprawling ecosystems of autonomous vehicles, robotic cells, and human operators working side by side across multiple production halls. And yet, despite their size and complexity, the rhythm of the process remains surprisingly calm. Everything flows according to plan, governed by Honda's unique lean manufacturing philosophy known as the Honda production system. The journey of a Honda car begins long before any metal is cut. It starts with production planning, a phase driven by market forecasts, dealer input, supply chain readiness, and model demand. Honda's plants operate on a build-to-order basis more than most automakers. That means production schedules are crafted based on actual customer orders and real-time market demand. This approach minimizes inventory waste and maximizes the efficiency of the supply chain. Once the schedule is locked in, suppliers across the globe begin preparing the thousands of components that will soon converge at the plant. Raw materials like steel and aluminum arrive at the factory in massive coils. These materials first enter the stamping department, a cavernous space filled with towering hydraulic presses. Each press is fed with sheet metal and fitted with enormous dies, complex mold tools shaped to form specific vehicle panels, such as hoods, doors, roofs, and fenders. The dies are interchanged automatically using massive overhead cranes and quick change systems, allowing the factory to shift between different vehicle models with incredible speed. These presses apply thousands of tons of force in milliseconds, transforming flat sheet metal into high-precision components with reinforced curves and load-bearing geometries. Each stamped panel is checked using template gauges or laser measuring arms to verify its accuracy against design tolerances. Honda's emphasis on dimensional precision at this early stage ensures that all panels fit perfectly during final assembly, which in turn improves both structural integrity and noise insulation. The stamped panels next travel to the welding shop, where the vehicle's skeleton, known as the body in white, is assembled. This stage is a symphony of automation. Dozens of robotic arms arc and swivel across each cell, welding panels together with pinpoint accuracy. These arms are fitted with spot weld guns, seam welders, laser cutting tools, and even rivet actuators, all pre-programmed for the vehicle model and trim level currently on the line. Guided by 3D coordinates, these robots can perform hundreds of welds in just a few minutes. Despite this high degree of automation, human workers play a vital role. Technicians monitor robotic operations, inspect weld seams visually, and perform manual welding in areas where robots cannot easily reach, such as complex internal joints or tight cavities. Importantly, Honda applies its stop-the-line authority in this department. Any associate who detects an issue is empowered to halt the line and initiate corrective measures immediately. This is part of Honda's respect for humanity approach, trusting operators not just to follow instructions, but to contribute actively to product quality. Once the weld shop produces a complete body shell, it enters the sealing and corrosion protection area. At this stage, structural adhesives and sound dampening materials are applied to critical areas of the body, such as the floor pan, roof seams, and door frames. These materials increase rigidity, improve crash performance, and reduce road noise. Seams are also sealed with flexible gaskets to protect against water ingress. After sealing, the body is conveyed to the paint shop, one of the most technologically advanced sections of the plant. Before any color is applied, the car is submerged in a series of cleaning and surface preparation baths. These include alkaline washes, acid baths, and a crucial e-coating step, in which the entire body is dipped in an electrically charged primer solution. The electrical current causes corrosion-resistant particles in the bath to bond uniformly with the metal, even in hard-to-reach crevices and weld joints. Once the e-coat is cured in an oven, the body enters a clean room environment for the color painting process. Robotic arms with electrostatic spray guns apply the primer, base coat, and clear coat in successive layers. Each layer is air-dried or heat-cured to ensure optimal adhesion and durability. Honda's paint robots use feedback-controlled nozzles that adjust spray patterns dynamically, based on body shape and angle, reducing overspray and minimizing environmental impact. Between layers, the vehicle is visually inspected under specialized lighting conditions. Technicians look for drips, dust contamination, and color uniformity. If any issues are found, the body is flagged for manual repair, which may include sanding, buffing, or repainting a specific panel. Once painting is complete and the final clear coat has cured, the body is ready for general assembly, the stage where it transforms from a painted shell into a fully functioning automobile. Before reaching the general assembly line, however, many key sub-assemblies are built in parallel feeder lines located throughout the plant. These include engine and transmission modules, suspension components, dashboards, interior trim sets, seat assemblies, and wiring harnesses. Honda practices a synchronized sub-assembly strategy. Each of these components is produced and sequenced in real time to meet the exact build order of the cars progressing down the main assembly line. That means if car number 287 is a Honda Accord hybrid in touring trim, every part of that specific configuration is queued and ready to install by the time the body reaches the relevant station. When the painted body reaches the main assembly line, it is mounted onto a moving conveyor system. This conveyor will carry the vehicle through dozens of stations, each performing a specific set of installations or tests. The first few stations focus on interior preparation. Sound deadening mats are applied to the floor. Wiring harnesses are routed through the firewall and chassis, and the dashboard is bolted into place. Honda uses pre-assembled dashboard modules, which include the instrument cluster, HVAC system, infotainment screen, and most switches, all pre-tested before installation. This reduces line complexity and improves consistency. Seats, carpeting, door panels, and airbags follow shortly after. At every step, workers use a system of digital instructions, torque control tools, and pick-to-light part bins to ensure that the right part is used and installed to the correct specification. Honda's goal is zero deviation from build order, even in mixed model lines, producing different trims every few minutes. As interior installation continues, the process becomes more intricate. With the dashboard now secured, the vehicle receives its electrical control units, sensors, and remaining interior electronics. These are connected to the pre-installed wiring harnesses using color-coded, click-locked connectors that help eliminate the possibility of human error. Specialized quality control stations may test critical modules immediately after connection, especially airbag sensors and crash detection systems, to ensure they are responsive and correctly integrated into the vehicle's network of ECUs. Following this, attention turns to glazing and weather sealing. Robots or trained technicians carefully install front and rear windshields, applying adhesive in a uniform bead to ensure a perfect seal. The installation is timed precisely as the adhesive cures rapidly. Door windows, quarter glass, and side mirrors are added next, with their mechanisms tested on the spot to ensure smooth operation. Throughout this process, jigs and fixtures are used to maintain tight tolerances between the panels and glass, ensuring aerodynamic integrity, road noise insulation, and weather protection. The vehicle then reaches one of the most pivotal points in the production process, the powertrain marriage. As the body travels down the assembly line, a pre-assembled drivetrain module consisting of the engine, transmission, front or all-wheel drive differential, and suspension subframe arrives underneath on a separate conveyor. The marriage station uses synchronized hoists and laser-guided platforms to lift the body and lower it gently onto the drivetrain assembly. Once aligned, operators bolt the body to the subframe using hydraulic torque tools, which log each torque application in real time for quality traceability. The process of mating the body to the chassis and powertrain is more than a mechanical operation. It's an integration of identity. From this moment, the car ceases to be a shell and becomes a functional vehicle. After the marriage, systems are connected The fuel lines, brake lines, wiring looms for sensors and control modules. Axles are bolted in. Radiators and intercoolers, along with their coolant hoses, are fitted. Exhaust systems are clamped into place and routed along the underbody using guides to prevent rattle or contact with heat-sensitive zones. Next come brake systems and suspension components. Brake calipers and discs are attached at each corner, followed by routing and fastening of hydraulic lines. ABS sensors and wheel speed sensors are snapped into their mounts, and their cables are clipped securely to avoid movement. Meanwhile, shock absorbers, coil springs or struts are fastened to the body using calibrated robotic arms or torque-controlled tools operated by line workers. These fasteners are critical as they influence ride quality, safety, and steering behavior. The wheels and tires, pre-mounted and balanced in a separate line, are then delivered just in time to the vehicle. They are aligned to the hub assemblies and fastened using pneumatically powered tools equipped with digital torque sensors. Each wheel torque is logged and checked against specifications. Even minor deviations trigger alerts. For instance, over-tightening a lug nut can damage threads or warp brake rotors, so precision is not optional. By this stage, the vehicle is mechanically complete, but not yet operational. It now passes into a startup and calibration zone, where the first true interaction between systems begins. Trained technicians perform a key-on sequence where all electronic systems are activated. This step includes powering up the main vehicle bus, initializing communication between ECUs, and performing a cold test of lighting systems, instrument clusters, wipers, and cabin electronics. The technician uses a diagnostic console to verify proper communication between modules and applies any last-minute software updates if required. Once the vehicle's systems are verified and error-free, the engine is started for the first time. A moment that is both mechanical and symbolic. As the engine cranks and catches, onboard diagnostics immediately monitor oil pressure, exhaust emissions, idle speed, coolant flow, and electrical charging. If any of these parameters fall outside of the calibrated range, the system flags the vehicle for further inspection. For hybrid models, the electric drive system may initiate instead, with the gasoline engine starting only after the battery's state of charge reaches a specific threshold. After the successful start, the car enters the rolling road test or chassis dynamometer. Here, it is strapped to large rollers that simulate road conditions. The car is driven through a standard cycle of acceleration, braking, shifting, and cruising, all while remaining stationary. This test evaluates key systems, including ABS, traction control, throttle response, gear engagement, hybrid transitions, and engine tuning. Sophisticated sensors and computers monitor hundreds of data points per second, ensuring the vehicle performs exactly as designed. Following the rolling test, the vehicle undergoes a headlight alignment and safety calibration station. Here, laser-guided systems measure the alignment of headlamps, and adjustments are made to meet both manufacturer and regional regulations. Advanced driver assistance systems such as lane keeping assist, adaptive cruise control, and forward collision warning are also calibrated at this point. This is accomplished using visual targets placed at known distances and angles in front of the vehicle, allowing cameras and radar units to learn their field of vision relative to the car's center line. Once these tests are complete, the vehicle proceeds to the water leak test booth, a sealed chamber equipped with an array of high-pressure water jets. For several minutes, water is sprayed at every angle, above, below, and from the sides, mimicking hurricane-force rain. Technicians inspect the cabin interior afterward for leaks, particularly around window seals, sunroofs, and door frames. Any sign of moisture sends the vehicle to a sealing team for immediate remediation and retesting. The car now moves into the final inspection area, often referred to as the white light tunnel. This zone is illuminated by intense, color-corrected lighting systems that reveal even the smallest defects in paint, fitment, and alignment. A team of inspectors walks around each vehicle, using mirrors to check lower panels, feelers to check panel gaps, and gauges to measure surface flushness. They assess the finish of paint, the gloss consistency, the evenness of door gaps, and the snugness of interior trim. Particular attention is paid to areas around weld joints, door hinges, and tailgate edges where minor misalignments can occur. Each inspector has the authority to flag the vehicle for any observed issue, no matter how small. Flagged cars are moved to a rework area where expert technicians resolve any concern before the vehicle can be released. Rework stations are not viewed negatively. They exist to ensure that every vehicle that exits the factory is indistinguishable from one that passed cleanly through all stages. After final inspection, the vehicle is prepared for delivery. Protective plastic sheeting is applied to painted surfaces and interior areas prone to contact during transport. The car is then driven to a shipping lot, where it is scanned into inventory and parked according to destination. Vehicles headed for domestic markets are grouped by dealership region and loaded onto transport carriers, while those bound for international markets are routed toward ports and loaded onto ships. The Honda factory's job may seem finished here, but in truth, its responsibility continues well beyond the factory gates. Each car's production data, including every torque value, software version, fluid fill level, and test result, is linked to its unique vehicle identification number and stored securely in Honda's manufacturing cloud. If an issue ever arises in the field, Honda can trace it back to the exact moment and operator involved in the car's creation. To witness the making of a Ford vehicle is to observe the evolution of industrial craftsmanship, a living embodiment of the assembly line system first pioneered by Henry Ford over a century ago, and refined today into a symphony of automation, digital intelligence, and human engineering. In modern Ford factories, like the Rouge Complex in Dearborn, Michigan, or the Oakville Assembly Plant in Ontario, production isn't simply about building cars. It's about orchestrating a precisely timed flow of materials, people, and machines that together transform raw components into advanced, drivable technology. The process begins long before the first bolt is turned or the first panel is stamped. The foundation of Ford's modern production system lies in rigorous planning and global coordination. Ford operates with a just-in-time and just-in-sequence supply chain strategy, meaning that materials and components arrive at the factory floor moments before they are needed. This eliminates the need for large stockpiles of inventory and increases the plant's flexibility to respond to changes in production schedules or model configurations. Planning starts with demand forecasting and order management. Using a centralized production planning system, Ford determines what models, trims, colors, and drivetrain variants will be built on any given day based on global dealer orders, regional demand patterns, and parts availability. This build mix is then converted into a master schedule that guides every action in the plant, from how robots are programmed, to which parts are loaded into which bins on which carts. At the heart of every Ford plant lies the stamping facility, where large rolls of sheet metal, primarily steel and aluminum, are cut and formed into individual body panels. These sheets arrive from external suppliers and are checked for thickness, flatness, and coating quality before entering the production line. Inside the stamping area, massive hydraulic or mechanical presses, sometimes up to 30 feet tall, use high tonnage force to shape the sheets into components such as hoods, roof panels, fenders, doors, and floor pans. Each stamping press contains tool and die sets, which are the sculpted steel molds that give shape to the metal. Changing these dies can take several hours on older systems, but Ford's modern plants use quick change tooling and automated die swapping cranes, allowing multiple model variants to be stamped in a single shift. Once stamped, each panel is inspected using automated vision systems and tactile measuring tools to ensure dimensional accuracy and surface quality. These stamped parts are then sent via conveyor or robotic shuttle to the next critical phase: body construction. In the body shop, robots dominate the floor. Here, the car's skeletal structure, called the body in white, is assembled from stamped panels. Using a combination of spot welding, MIG welding, and adhesive bonding, robots join together hundreds of individual panels to form a rigid structure that meets crash and durability standards. Each robotic cell is carefully synchronized, with arms moving in mirrored patterns to weld seams, attach reinforcements, and secure structural elements like the rocker panels and cross members. The entire body structure is periodically scanned with laser measurement systems. These 3D scanners create digital models of the assembled body to verify that it remains within tight tolerances. Even the smallest variation, fractions of a millimeter, could cause issues with later stages, such as door alignment or windshield fitting. If a body is found out of spec, it is automatically flagged and removed from the line for correction or further inspection. While the robots do the bulk of welding, human operators in the body shop play crucial roles. Some welds require access to tight spaces that robots can't easily reach. In addition, skilled technicians perform tactile inspections, feeling for uneven surfaces, sharp edges, or anomalies that a vision system might miss. They are also empowered to stop the line using an and-on system, a visible alert mechanism that signals an issue requiring immediate attention, a practice inherited from lean manufacturing disciplines. Once the body is complete, it's sent to the paint shop, a sealed and environmentally controlled environment that is perhaps the most intricate and sensitive area of the plant. But before paint can be applied, the body must be cleaned, prepped, and protected. It first enters an electrodeposition tank, or e-coat bath, where it is submerged in a liquid anti-corrosion primer. An electric current causes this primer to bond uniformly to every surface of the body, inside and out, including hidden cavities where rust could otherwise form over time. After curing in an oven, the body moves into a multi-stage painting process. Robots apply layers of primer, color, and clear coat using electrostatic spray guns, which attract paint particles to the metal surface like a magnet. The advantage of this method is increased efficiency and reduced overspray, leading to lower paint consumption and a cleaner environment. Ford's paint booths are equipped with air filtration and humidity control systems to eliminate dust or contaminants that could mar the finish. At each stage, lighting conditions are precisely calibrated to reveal imperfections, and technicians are stationed throughout the booth to perform quality checks. If a blemish is detected, a run in the paint, an uneven finish, or a missed spot, the vehicle is diverted to a paint repair zone where the affected area is wet sanded, resprayed, or polished by hand to meet Ford's appearance standards. After the final coat, the body undergoes a final curing process in a high-temperature oven to harden the paint and create a durable, glossy finish. The now fully painted vehicle shell, known as the trimmed body, advances to the general assembly line. This is the most labor-intensive section of the factory, where machines and humans collaborate closely. Unlike the body shop, where robots dominate, the general assembly area relies more heavily on human hands, precision tools, and ergonomic aids. The car body is mounted on a moving conveyor system known as a skillet line or friction drive platform, which carries the car through a series of workstations at a constant, carefully controlled speed. Assembly begins from the inside out. First, teams install insulation pads and sound deadening materials. Next, wiring harnesses, which form the car's electrical nervous system, are laid out and clipped into position along the floor, firewall, and side panels. Each harness contains dozens of connectors that will link to ECUs, lighting elements, climate controls, sensors, and powertrain systems. Proper routing and fastening of these cables are essential for both performance and safety, so visual checks and scanner-based validations are used at multiple points. Then comes the dashboard module, which is typically pre-assembled in a nearby subline. It includes the steering column, HVAC ducts, infotainment screen, and instrument cluster. This large component is inserted into the cabin as a unit using mechanical arms and then bolted into place. Seats, carpeting, interior trim panels, seatbelt retractors, airbags, and roof liners follow, each added in a precise order, with visual and tactile inspections performed continuously to ensure flawless fit and finish. Throughout this interior build process, Ford uses error-proofing tools such as torque-controlled wrenches, pick-to-light bins, and vision-guided assist arms. Every torque application is digitally logged. If a bolt is over or under-torqued, the system automatically halts the line and flags the issue. This traceability is vital, not only for quality assurance, but also for future diagnostics should the vehicle need service or become subject to a recall. Continuing from the general assembly line, the next transformative step in the creation of a Ford vehicle is the marriage of the painted body with the powertrain and chassis systems, a defining moment in every car's life on the line. As the body shell makes its way along the conveyor, the fully assembled engine, transmission, suspension, and front subframe approach from a lower parallel track. These components, built and tested in a separate sub-assembly area, are synchronized to arrive at the exact moment when the body reaches the marriage station. Here, specialized lifting systems raise the powertrain module from below while the body is gently lowered from above. Technicians, supported by robotic arms and torque-controlled tools, fasten the body to the chassis at critical mounting points. This precise alignment is essential. It determines the geometry of the suspension, the drivetrain angles, and even the behavior of noise and vibration through the cabin. Fuel lines, coolant hoses, drive shafts, brake lines, and wiring harnesses are then connected between body and chassis, integrating the mechanical and electrical systems into a unified vehicle. After the marriage, the vehicle receives its cooling system, air intake, and exhaust components, followed by fluids, including engine oil, brake fluid, transmission fluid, and coolant, all filled using automated dispensers that monitor volume, pressure, and flow rate. These filling stations ensure consistency down to the milliliter, and if there is any deviation from the programmed values, the system stops the process and flags the vehicle for investigation. With the engine installed and fluids topped off, the vehicle is now nearly complete. It receives its wheels and tires, which are pre-mounted, balanced, and matched to the specific trim and model variant. These are installed using torque monitoring impact wrenches, and the system logs each wheel's torque values in the vehicle's digital build record. Exterior components such as bumpers, lights, badges, grille assemblies, and mirrors are now added, bringing the vehicle's final form into view. At this stage, the car has all its physical components, but it still needs to come to life. The next section of the line is dedicated to initial startup and systems calibration. A technician connects the vehicle to a diagnostic console and performs the first ignition sequence. This process powers up the ECUs, activates safety systems, and starts the engine. Immediately, a flood of data is captured: oil pressure, engine RPM, voltage, emissions readiness, and more. The technician watches for warning lights, verifies software synchronization, and confirms that all onboard systems are responsive. If all readings are within specification, the vehicle advances to functional testing, where every major system, lights, brakes, steering, wipers, infotainment, HVAC, and electronic safety aids, is tested in a rapid, choreographed routine. Ford technicians use handheld devices and sensor panels to trigger functions and confirm their proper operation, all while the vehicle moves slowly along the inspection path. Any anomaly here diverts the vehicle to a diagnostics bay for further analysis. The story of an H2R does not begin on the assembly line. It begins much earlier, within the metallurgical divisions and materials labs that prepare the raw constituents of the motorcycle's essential components. At this initial stage, the journey starts with a block of high-tensile steel alloy, specifically formulated for the H2R's trellis frame. This isn't ordinary steel. Kawasaki engineers designed the alloy composition to maximize tensile strength while balancing torsional rigidity and ductility. Sheets and tubing are delivered to the fabrication facility in precisely measured cuts, each one traced through an internal lot tracking system for complete traceability. Within the factory, the raw frame tubing undergoes cold drawing, a process that pulls the steel through dies to fine-tune its dimensions and surface integrity. Cold drawing is chosen specifically because it preserves mechanical strength while yielding tight dimensional tolerances, which are critical for the trellis frame's intricate geometric structure. Robotic armatures position each steel tube beneath automated laser cutting heads that slice the tubes into exact segments, using CNC-defined angles to ensure proper later fitment during welding. The accuracy here is staggering. Deviations beyond 0.1 millimeters trigger alerts in the system, halting the production cell for inspection. These cut tubes are then transferred via automated conveyors to a robotic frame welding station. Unlike mass-market motorcycle frames, the H2R's frame is entirely hand-welded, albeit with robotic support for fixturing and alignment. Skilled technicians, each trained for months on frame-specific geometries, perform manual TIG welding to fuse the chromoly steel components together. This welding process isn't just about joining metal. It's a delicate operation, balancing thermal input and cooling rates to avoid internal stress or warping, which could compromise high-speed stability at over 300 kilometers per hour. Once the frame is assembled, it enters a dimensional verification stage utilizing 3D laser scanning. The scanning head, mounted on a 6-axis robotic gantry, creates a digital twin of the physical frame, comparing it to the original CAD model within fractions of a millimeter. If the frame passes all checks, it moves to a powder coating line where it is electrostatically coated and oven cured at controlled temperatures. The specific gloss and hardness of the black frame coating are chosen for both heat resistance and resistance to rock chips and vibration-induced wear. Meanwhile, in another section of the plant, the supercharged engine, the beating heart of the H2R, begins its life in the engine assembly hall. This hall is a restricted environment, temperature and humidity controlled, and acoustically insulated from the rest of the plant. The reason is simple. The inline 4-cylinder engine that powers the H2R is not just another power plant. It's an ultra-high performance 998cc unit, force-fed by a centrifugal supercharger capable of spinning at up to 130,000 RPM. Such precision demands a sterile, meticulously maintained production environment. Engine block castings arrive from Kawasaki's dedicated foundry, having been machined to spec using 5-axis CNC centers. These blocks are inspected using ultrasonic resonance techniques to detect subsurface anomalies that cannot be seen visually or through surface scanning. If the casting passes inspection, it is mounted onto an engine cradle fixture, and the first stage of assembly begins. The installation of crankshaft bearings. Each bearing shell is hand micrometered and color-coded marks are applied to designate their oil clearance class. This step is crucial because the H2R engine tolerances are far tighter than in commuter bikes. The goal is minimal oil film thickness for maximum responsiveness without inducing friction-related failures. After the bearings are installed, the forged steel crankshaft is delicately lowered into the block. This crankshaft, balanced to aerospace-grade tolerances, is laser etched with its unique serial number for tracking and quality assurance. Next, titanium connecting rods and forged pistons are assembled offline on dedicated piston rod mating benches. Each piston is weighed and matched to its rod to within 0.5 grams to ensure uniform reciprocating mass balance. Piston rings are installed using rotary ring expanders that ensure even pressure and no deformation. The piston assemblies are then inserted into the engine block using hydraulic-assisted ring compressors, and the crankshaft is rotated by hand through a flywheel fixture to ensure smooth, unimpeded movement. Even the tiniest resistance would be flagged as an indicator of misalignment or contamination. Once the bottom end is secured and torqued in a cross pattern using digitally calibrated torque wrenches, attention shifts to the cylinder head. The H2R cylinder head is a complex component, machined with pent roof combustion chambers, large titanium valves, and dual overhead camshafts. Valve springs are installed using a pneumatic valve spring compressor, and valve lash is adjusted using precision shims measured to within hundredths of a millimeter. Camshafts, hardened and micro-polished, are mounted on journal caps and rotated to align with timing marks on the crank. The timing chain, a double roller unit, is fed through a guide channel and connected to the crank sprocket, then tensioned using a hydraulic chain tensioner preloaded with assembly oil. Once aligned, the engine is rotated again by hand, and valve timing is confirmed using a laser cam phase analyzer that calculates exact intake and exhaust overlap degrees. Now comes the installation of the supercharger, the defining feature of the H2R. The supercharger is assembled in a separate cleaned cell. Its impeller, machined from a single billet of aluminum, is balanced using high-speed spin balancers before being mounted to the planetary gear drive. The planetary gear unit, in turn, is gear-driven from the crankshaft and is fitted with helical cut gears to reduce noise and increase torque handling. Once mated, the entire supercharger is tested in a closed-loop bench system, where it is spun up using a drive motor to simulate load and airflow output. Only if it meets the volumetric efficiency thresholds is it approved for installation onto the engine. As the supercharger is bolted onto the engine using a dedicated torque fixture, the entire power plant assembly is now ready to move to the dyno test cell. But before that happens, it's moved to a pre-test station where all fluids are filled. High temperature synthetic oil, long life coolant, and a special break-in fuel blend optimized for seating piston rings under load. The engine is then mounted into a test cradle wired with sensors and bolted to an eddy current dynamometer. Here, engineers run the engine through a programmed break-in cycle, gradually increasing load and RPM while monitoring combustion pressure, knock, oil pressure, and temperatures. Each engine must meet specific power output metrics before it's allowed to leave the test cell. For the H2R, this figure is over 310 horsepower measured at the crankshaft. Engines falling short are automatically rejected and moved to a forensic diagnostics bench where engineers determine whether the issue lies in fuel delivery, boost pressure, valve timing, or internal mechanical components. Once the dyno-tested engine has passed all performance and durability checks, it is removed from the test cradle and placed onto a specially designed rolling engine dolly. This dolly is more than a simple transport mechanism. It interfaces with hydraulic lift systems, allowing technicians to tilt, raise, and lower the engine precisely for the upcoming frame integration process. Before reaching the frame marriage station, however, the engine is routed through a pre-integration checkpoint where a technician conducts a final surface inspection, verifying all sealing surfaces, torque marks, and component connections. At this stage, all auxiliary components, such as the alternator, Starter motor, oil cooler, and coolant hoses are pre-mounted to reduce complexity during frame insertion. Meanwhile, the painted and fully inspected trellis frame, already cured and cooled from its powder coating process, is mounted on an assembly jig at the chassis preparation station. Here, the steering head bearings are greased and installed using an automated bearing press that ensures equal pressure distribution to avoid warping or damage. Into this steering head, the forged aluminum triple clamps are inserted and torqued to specification using a digital torque wrench with data logging capability. The handlebar mounts are temporarily attached for alignment purposes, but the handlebars themselves will come later in the line. At the engine marriage station, the prepped engine and trellis frame are brought together. A hydraulic lift slowly raises the engine into position beneath the frame, while two alignment pins guide the engine mounting points into perfect register with the frame brackets. 4 titanium bolts, lighter and stronger than traditional steel, are inserted and torqued in a diagonal sequence to avoid any stress concentrations. This step marks the true structural birth of the motorcycle. From this point onward, the machine is no longer a collection of parts. It is a unified mechanical system. With the engine mated to the frame, the motorcycle chassis is now placed onto the primary assembly line, an overhead conveyor system that moves each bike along a guided rail through multiple semi-automated workstations. The first station is the front suspension installation area. The H2R utilizes massive 43mm KYB AOS2 forks, which are fully adjustable and coated with a low-friction DLC layer. Each fork is filled with a precise volume of high-performance suspension oil using a vacuum fill station, then sealed and compressed to check for internal leaks. Once ready, the forks are inserted into the triple clamps and aligned using a digital laser alignment rig to ensure perfectly parallel orientation. Following this, the front wheel assembly, which consists of a Marchesini forged aluminum rim, dual 330mm Brembo discs, and a Pirelli slick racing tyre, is rolled up to the workstation. The wheel is mounted onto the axle, and the Brembo M50 monoblock calipers are installed with anti-vibration shims. The brake lines are routed along the fork legs using pre-formed clips, and each banjo bolt is torqued and marked with a color-coded paint pen for visual confirmation of completed steps. Parallel to the front suspension assembly, another robotic cell is preparing the swing arm subassembly. The H2R's single-sided swing arm is a hollow, forged aluminum unit with internal stiffeners. It is laser welded and then machined to accept the axle carrier and chain adjusters. Once verified for alignment using a 3D measurement gantry, the swing arm is connected to the frame using a solid pivot bolt, then connected to the rear shock. The rear suspension is a gas-charged KYB monoshock unit, also fully adjustable, and mounted on a rising rate linkage system for progressive damping under heavy loads. With front and rear suspension in place, the H2R is now a rolling chassis capable of supporting its own weight. At this point, the conveyor system gently lowers the motorcycle onto a rolling dolly with locking casters, freeing up the overhead rail for the next unit. The rolling chassis is pushed manually to the next station, the electronics and wiring harness integration bay. Unlike lower-tier motorcycles, where wiring is often installed as a single unified harness bundle, the H2R employs a modular wiring system. Multiple sub-harnesses for the engine control unit, traction control system, data logger, ABS system, and dashboard are installed independently, with each module having its own waterproof snap lock connector. The main harness is routed through the spine of the frame, secured with P-clips and thermal-resistant sleeves to protect from engine heat. Each connector is scanned using an RFID tool to ensure proper mating, and the system performs a low-voltage continuity check before proceeding. Once the electrical systems are routed, the control units are mounted in their designated locations. The inertial measurement unit is mounted beneath the seat. The ECU is housed in a vibration-isolated tray behind the headstock, and the quick-shifter sensor is attached to the gear linkage rod. The dashboard, a full-color TFT display, is installed into the carbon fiber front cowl support and wired into the CAN bus network. With control systems in place, the next stage is the installation of the fuel system. The H2R's fuel tank is not merely a container, it is a shaped aluminum shell with internal baffles and foam inserts designed to reduce sloshing during extreme cornering. Each tank is pressure tested at 1.5 times normal operating pressure to check for leaks. A high-flow fuel pump is mounted internally, and the tank is lined with a corrosion-resistant coating that protects against ethanol degradation. The tank is installed onto rubber isolators on the frame spine and connected to the fuel rail via quick disconnect couplings. Underneath the fuel tank, the intake system comes together. The airbox is a sealed high-capacity plenum chamber designed to handle pressurized air from the supercharger. It features a ram air intake duct and a high-flow air filter made from synthetic fibers. Sensors for intake air temperature and pressure are inserted, and the throttle bodies, ride-by-wire, electronically controlled units, are bolted directly to the intake ports. The supercharger outlet feeds directly into the airbox, and a blow-off valve is installed to regulate excess pressure during throttle closure. Once all intake and fuel connections are secured, the exhaust system is installed. The H2R utilizes a titanium exhaust header that is hand-welded and purge-welded from multiple conical sections. Each pipe is flow bench tested prior to assembly to ensure even back pressure across all 4 cylinders. The exhaust system includes a collector and a short, undertail silencer, designed to reduce weight and maintain optimal power output with minimal restriction. Sensors for oxygen content and exhaust temperature are threaded into the headers and linked to the ECU. At this point, the bike is fully assembled mechanically, but bodywork has not yet been applied. That comes in the next segment of the production process. But before that, the motorcycle moves into the first startup and diagnostic bay. Here, technicians connect a master diagnostic tablet to the ECU via the OBD port. The system runs a full checklist, verifying sensor functionality, fuel pump pressure, throttle actuator operation, and system voltages. Once verified, the bike is started for the very first time. This initial start is a tense and critical moment. The technician listens closely for any abnormal mechanical noise, monitors the idle speed, checks for warning lights on the TFT display, and ensures that oil pressure rises immediately upon startup. The engine is allowed to idle until it reaches operating temperature, during which time the cooling fan, radiator circulation, and combustion balance are all evaluated. Any deviation from spec prompts an immediate stop and transfer to the diagnostic cell for further investigation. If the startup test is successful, the motorcycle is shut down and moved to the fluid leak test station. Here, a UV dye is added to the oil and coolant systems, and the bike is placed under black light to reveal any possible leaks at hoses, joints, or gaskets. Pressure is applied to the cooling system using a sealed radiator cap rig, and the oil system is pressurized via a pneumatic pump. This ensures that even micro leaks are detected before the bike proceeds to final cosmetic assembly. With all functional systems now tested and verified, the powertrain mounted, the electronics integrated, and the fluids checked for sealing integrity, the Kawasaki Ninja H2R is finally ready to receive what many consider its most striking feature, its full carbon fiber bodywork. Unlike plastic fairings found on standard motorcycles, the H2R's aerodynamic surfaces are crafted entirely from pre-preg carbon fiber panels that are formed, trimmed, and finished in a tightly controlled composites facility within Kawasaki's aerospace division. Each carbon panel From the sculpted front cowl to the aggressive side fairings to the single-piece tail section, begins life as a sheet of carbon fiber impregnated with epoxy resin. These sheets are hand-laid into CNC machined aluminum molds, layer by layer, with careful attention to fiber orientation and overlap. This layup process determines the final strength and stiffness of the component. And technicians follow a digital blueprint showing precisely where each ply must be placed. Once the layup is complete, the mold is vacuum sealed inside a heat-resistant bag and placed into an autoclave. In the autoclave, the part is subjected to high temperature and pressure, curing the resin and fusing the carbon plies into a single monolithic shell. The process takes several hours, during which the exact pressure and thermal cycle are carefully controlled and logged. After curing, the mold is cooled and the part is demolded and sent to the trimming station. Here, 5-axis CNC water jet cutters remove excess material and create mounting holes, while laser measuring arms verify dimensional accuracy down to fractions of a millimeter. Once trimmed, each body panel goes through a polishing and surface inspection process. Technicians in cleanroom suits buff the surface to prepare it for paint, but for the H2R, this isn't just a cosmetic paint job. It's a defining visual signature. The entire carbon shell is sprayed with Kawasaki's proprietary mirror finish paint, a multi-layered formula that gives the H2R its iconic black chrome look. This paint contains a layer of silver-infused base coat that reflects light like a mirror, followed by multiple layers of clear coat that are wet sanded and polished between applications. The painted carbon fiber parts are then cured in low dust ovens at carefully controlled temperatures. When they emerge, they undergo final inspection under polarized lighting to reveal any imperfections invisible to the naked eye. Only when each piece passes this inspection are they released to the final cosmetic assembly line. Back in the main assembly hall, the rolling chassis is now stationed at the fairing installation bay. Here, a team of 2 technicians works on each unit, using soft-gloved hands and non-marring tools to install the carbon fiber bodywork. The upper cowl is mounted first, secured to a lightweight subframe using vibration-resistant fasteners. The side fairings follow next, installed with grommeted bolts and lined with thermal insulation on the inner surfaces to protect against engine heat. The winglets, a defining aerodynamic element of the H2R, are bolted to the sides of the front fairing using precision jigs. These carbon fiber strakes generate downforce at high speeds and are carefully aligned to match the factory's computational fluid dynamics models. The tail section, which includes the seat pan and integrated rear lights, is installed last. It slots over the subframe like a precision machined cover, secured with hidden fasteners that leave the outer surface clean and uninterrupted. The final visual pieces include the windscreen, made of high-impact acrylic formed over a heated vacuum mold, and the mirrors, which are unique to the H2R in that they are replaced by aerodynamic blades due to its track-only designation. These aerodynamic devices further contribute to the overall downforce and high-speed stability of the motorcycle. With all external components now in place, the motorcycle advances to the lighting and display verification stage. Even though the H2R is not street legal and lacks conventional headlamps, it still features essential lighting systems for track use, including brake lights and dashboard illumination. A diagnostic terminal is connected once more to the onboard electronics, which triggers all LEDs, signal displays, and digital readouts. Any pixel dropout or timing issue in the TFT display is immediately flagged, and the dashboard is swapped out before the motorcycle proceeds. The next phase is torque auditing. Using a handheld digital wrench interface, a technician rechecks every critical fastener on the motorcycle, referencing a torque database specific to the H2R. Each bolt, from the engine mounts to the suspension linkages to the brake calipers, is checked, and the data is wirelessly transmitted to a central quality control server. This system creates a complete torque audit trail for every unit, ensuring that no component is under or over-tightened, which could lead to safety issues under track loads. Following torque audit, the motorcycle is moved to the final mechanical verification bay, a rolling road dynamometer enclosed in a safety chamber. Unlike the earlier engine dyno test, this test evaluates the entire drivetrain system, including wheel alignment, chain tension, gearbox operation, and traction control responsiveness. The motorcycle is strapped down securely onto a rotating drum, and a technician rides the bike through a simulated series of track laps using paddle inputs to shift gears, apply throttle, and trigger braking. The onboard IMU and traction control system are monitored in real time to assess how the electronic aids respond under aggressive load transitions. One particularly crucial part of this test is the quick shifter evaluation. The H2R uses a bidirectional quick shifter that allows for clutchless upshifts and downshifts under load. The dyno software simulates various throttle and RPM combinations while the technician triggers shifts. Sensors measure delay time between shift input and gear engagement, and the ECU adjusts the ignition and fuel cut profile dynamically. If lag or false neutrals are detected, the quick shifter sensor or shift drum is re-inspected. Following dyno verification, the motorcycle is shut down and allowed to cool under controlled airflow. It is then cleaned using ionized air to remove any dust or debris collected during testing and rolled into the inspection corridor, a quiet, well-lit area reserved for aesthetic and dimensional verification. Here, trained inspectors examine every square centimeter of the motorcycle's surfaces under fixed-angle lighting rigs that highlight reflections and contours. They check for paint consistency, panel fitment, fastener flushness, and emblem placement. The final inspection is concluded with a checklist signed by a master inspector who holds clearance to certify H2R units for packaging. A QR-coded certification tag is applied beneath the seat, containing digital records of every test, torque, spec, and visual check the motorcycle has passed. This tag remains with the bike for life, accessible by service centers and authorized Kawasaki technicians. At this point, the motorcycle is ready for crating and shipping, but before that occurs, a factory photographer captures high-resolution images of each unit for archival and legal purposes. These photos document the visual condition at the time of shipment and are stored alongside each VIN's production history. The H2R is then rolled into the final staging area, a climate-controlled packaging room where each motorcycle is carefully enclosed in a custom-built steel and wood crate. The front wheel is braced, the suspension compressed slightly with straps, and the bike is cocooned in protective foam. Every surface prone to scratching is wrapped with a low-tack film. Accompanying the motorcycle is a documentation pack that includes a certificate of authenticity, a technical user manual, a tuning guide, and the special tools required for trackside maintenance. Now ready for departure, the crated H2R is scanned into the logistics database and scheduled for dispatch. Its destination could be a private collector's garage, a professional racing team's paddock, or a high-end performance dealer specializing in exotic motorcycles. Once the Kawasaki Ninja H2R has been crated and logged into the factory's outbound inventory system, its journey through the global supply chain begins. The finished motorcycle, now nestled inside a reinforced steel-tubed crate with engineered shock absorption inserts and padded contact points, is not treated like standard inventory. This is not mass market production. Each unit is registered and scheduled for delivery with the same level of care typically reserved for aerospace-grade cargo or high-value prototype machinery. The H2R crate is fitted with a tamper-evident seal and a GPS-enabled tracking unit. This small battery-powered device is embedded in the crate frame and continuously broadcasts location, temperature, and shock readings throughout the duration of the shipment. The goal is absolute transparency and control. Kawasaki's logistics division uses a centralized tracking portal to monitor every H2R in transit, ensuring that any anomaly, a sudden temperature spike, an excessive tilt angle during forklift handling, or an unexpected deviation from a scheduled route triggers a real-time alert and investigation. Within the Kawasaki factory's outbound logistics terminal, all outgoing H2Rs are staged in a secure area awaiting carrier pickup. This area is isolated from regular shipping docks and utilizes biometric access controls. When transport is scheduled, only certified freight handlers are permitted to load the crated bikes onto specialized trucks equipped with air ride suspension systems. These vehicles reduce vibration and road shock that could otherwise stress the precision-fitted carbon components or delicate electronics inside the crate. Each transport vehicle is assigned a specific destination hub, most commonly one of Kawasaki's global distribution centers. These hubs, located strategically in Europe, North America, the Middle East, and Asia, are more than just warehouses. They are hybrid facilities combining bonded customs zones, climate-controlled storage, and dealer preparation stations, all operating under strict quality assurance protocols. When a truckload of H2R units arrives at one of these hubs, the unloading process is supervised by Kawasaki regional logistics managers. Each crate is inspected for seal integrity and then scanned into the regional inventory management system using the embedded RFID and QR codes. For units destined for overseas markets, international freight forwarding is used. Crates are loaded into secure ISO shipping containers fitted with humidity control packs and shock-damping floor mounts. These containers are then booked onto cargo ships under insured, high-priority manifests. During ocean transit, the environmental monitoring systems embedded in the H2R crates continue logging data, which is uploaded via satellite uplink every 12 hours. When the containers reach port, customs clearance is expedited through Kawasaki's import-export licensing system, which pre-registers each motorcycle's VIN with the appropriate government authorities to simplify the paperwork associated with limited use non-street legal vehicles. Once the motorcycles arrive at their respective dealer prep centers, they are again moved using air ride trucks and secured holding bays. The dealer-level uncrating process is perhaps one of the most sensitive moments in the entire chain. These centers are equipped with padded flooring, overhead cranes, and specialized unboxing stations designed specifically for ultra-high performance motorcycles. Each crate is disassembled manually, using torque-limited tools to avoid overstressing any fastener. The protective wrap and foam buffers are removed, and a technician conducts a full visual inspection before any mechanical interaction occurs. At this point, the motorcycle is still in a semi-dormant state. While fully assembled at the factory, the H2R is shipped with several systems disabled or set to low activation mode. For example, the ECU is placed in a transport-safe state to prevent any unauthorized ignition or tampering during transit. The traction control system and launch control features are also disabled until activation codes are entered through the factory diagnostic tablet. These codes are provided only to certified Kawasaki race dealer technicians who have completed a specialized training program exclusive to the H2R platform. The first step during dealer prep is to activate the motorcycle's electrical systems. A lithium-ion high-output battery, which was shipped separately to avoid power drain or risk of damage, is installed using a torque-calibrated battery tray mount. The diagnostic tablet is then connected, and the technician runs a software handshake that reactivates the ECU, initiates a full sensor sweep, and calibrates the electronic throttle bodies to their neutral closed position. This is followed by a firmware update if required, ensuring that the bike is running the latest version of Kawasaki's proprietary control logic, an intricate blend of traction, wheelie, slide, and launch control algorithms designed for elite track use. Fuel is then added to the tank, typically a high-octane, ethanol-free race blend sourced by the dealer. This ensures consistent combustion characteristics for the first startup under the dealer's supervision. The cooling system is topped off with pre-mixed long-life coolant, and brake fluid levels are checked. While all systems were previously pressure tested at the factory, this step ensures that nothing has been compromised during transport. The first dealer-level ignition is performed under controlled conditions. The motorcycle is mounted on a paddock stand with wheel chocks and exhaust ventilation systems in place. The technician initiates the ignition cycle, monitors the startup process, and allows the bike to idle while all systems reach operating temperature. During this time, the technician observes engine temperature, oil pressure, throttle responsiveness, and warning indicators. Once warmed up, the throttle is blipped to ensure proper response from the supercharger system. A high-pitched whine confirms that the planetary gear-driven supercharger is spinning freely, and boost sensors are checked to verify pressure increase under transient throttle input. Next comes dynamic system calibration. The dealer technician enters a closed test loop menu via the diagnostic interface, and the motorcycle performs a series of controlled internal tests. These include throttle plate synchronization, IMU pitch and roll calibration, wheel speed sensor checks, and brake pressure modulation trials. These diagnostic steps ensure that all ride assist systems are correctly aligned and functioning before the motorcycle is released to the client. Before final delivery, cosmetic detailing is performed. The bike is cleaned using non-reactive anti-static cloths and waterless detailing sprays to preserve the mirror finish. Tire pressure is adjusted to the recommended range for track delivery, and chain slack is fine-tuned based on the factory's specification under rider weight simulation. The data logging module, if the customer has opted for the full telemetry package, is also installed at this stage, including its GPS antenna and onboard SD card reader. At this point, the motorcycle is ready for customer delivery, but the H2R is not simply rolled out onto the sales floor. In most cases, the delivery is either performed at a private unveiling event or within a dedicated performance showroom, often involving customer briefings, technical walkarounds, and personalized instruction. The purchaser receives a digital service log, a registration keycard for the diagnostic system, and, depending on region, a certificate of ownership detailing the motorcycle's serial number and place of manufacture. Some customers even receive a titanium plaque etched with their VIN, engraved at the factory using the same fiber optic laser that marks engine components. For customers intending to race the bike, additional services are offered. These include initial track setup, suspension tuning based on rider weight and intended circuit, and ECU mapping optimization. Kawasaki certified race engineers are sometimes deployed directly to high-profile clients to help integrate the bike into a team's racing fleet or private collection. In total, from the moment an H2R begins its life in the alloy preparation bay to the moment it is fired up in a client's garage or paddock, the process spans multiple continents, dozens of specialists, and a series of rigorously enforced quality checkpoints. No step is accidental. Every decision, from the type of crate to the orientation of the brake lines during shipping, is designed to protect and preserve the uncompromising nature of the Ninja H2R.